Good morning, ladies and gentlemen. Welcome to the ICoMPAC 2025, the 9th International Conference on Mathematics, Pure, Applied, and Computation, proudly hosted by the Mathematics Department of the 10 November Institute of Technology.
This program is sponsored by Prawatya Karsa Pradipta, Jagat Sanitasi Indonesia, Adiluhung Sarana Segara, Telkom Indonesia, and Boring AI. It is such a pleasure to see academics from various backgrounds gathered here for a shared purpose, to explore how mathematics and computation can drive positive change in our world. My name is Silma.
And I am Charles.
And we are honored to serve as the master of ceremony for today's program.
Ladies and gentlemen, this wonderful program is a remarkable collaboration between researchers across the world to highlight how mathematical and computational thinking can positively contribute to sustainable development.
Over the course of this program, we will hear from leading experts in pure and applied mathematics. The presentations, discussions, and exchange will enrich our understanding and foster new collaboration.
Before we begin, let us take a moment to give a warm welcome to our honorable guests. Firstly, Professor Agus Mohammad Atta, Vice Rector for Research, Innovation, Cooperation, and Alumni at ITS.
Professor Dr. Dawi Hidayati, Dean of the Faculty of Science and Data Analytics, ITS. Professor
Hongxi Lu, from National Taiwan University of Science and Technology from Taiwan.
Professor Tsuyoshi Miyazaki, from the National Institute for Material Science, Japan.
Associate Professor Dr. Rino Wanti, from Institute Technology 10 November from Indonesia.
Professor Agus Hassan, from the Norwegian University of Science and Technology, who's joining us online.
Associate Professor Didik Husnul Arif, Head of Mathematics Department at ITS.
Dr. Muhammad Iqbal, Chairman of ICoMPAC 2025.
Mrs. Insignor Anita Puji Utami, President Director of PT Adiluhung Sarana Segara, Indonesia.
Mr. Besar Yuninto Hidayat, Director of Prawatya Karsa Pradipta.
Mr. Badru Salam, Director of PT Jagat Sanitasi, Indonesia.
And all distinguished participants for joining us on-site or virtually. It is your contributions that bring this conference to life. To officially start our program with respect and gratitude, let us stand together to sing our national anthem, Indonesia Raya. This session will be led by Nabila Zahra Alfianti Timbuleng. We kindly invite all participants to please rise.
Thank you, ladies and gentlemen. Please be seated.
Proceed to our next agenda. We will formally open this program with opening remarks from Dr. Muhammad Iqbal, the chairman of ICoMPAC 2025. To Dr. Muhammad Iqbal, the stage is yours.
Okay, Assalamualaikum warahmatullahi wabarakatuh, and good morning. So, distinguished guests and respected Vice Rector, Professor Agus, and then esteemed keynote speaker, fellow research colleagues and participants, it is with great honor and heartfelt appreciation that I welcome you all to the 9th International Conference of Mathematics, Pure, Applied, and Computations, or ICoMPAC 2025, held from 22nd to 24 October 2025 at the Sheraton Hotel and Tower Surabaya and also ITS Surabaya. On behalf of the organizing committee and the Department of Mathematics, Institute Teknologi 10 November, I'm delighted to open this important event and extend our warmest greetings to all of you from Indonesia and from across the globe who have gathered here to share knowledge, explore ideas, and build meaningful collaborations. This year, ICoMPAC 2025 is held under the theme Mathematics and Computation for Sustainability, a theme that reflects not only the pressing global challenges we face, but also the crucial role that mathematics and computation play in addressing those challenges. From climate modeling, renewable energy optimization, and environmental data analysis to sustainable resource management and resilient infrastructure design. Mathematics stand at the heart of innovation for a sustainable future. We are truly honored by the presence of the Vice Rector, and whose leadership continues to inspire the ITS academic community to pursue excellence in research and international engagement. Thank you, Professor, for your continued support and for officially opening this conference later. ICoMPAC has grown steadily over the years, and its ninth edition, it continues to serve as a platform for open academic exchange in the field of pure mathematics, applied mathematics, and computational mathematics. This year's program features distinguished keynote speakers, a rich array of technical sessions, and carefully selected collection of peer-reviewed papers, each contributing to our understanding and application of mathematics in real-world contexts. And I would like to express my deepest gratitude to our scientific committees and reviewers for their dedication and critical insight, the authors and presenters today for their hard work and valuable contributions, and our keynote speaker for sharing their time and expertise, the organizing committee for their tireless efforts behind the scene. And of course, like this is our first time, we have our partners and sponsors for their continued support. To all participants, I encourage you to engage actively to challenge ideas, to ask questions, and to connect with one another. That use us this opportunity not just to present our research, but to strengthen the global mathematical community and drive forward the missions of sustainability. Once again, welcome to ICoMPAC 2025. May this conference be insightful, inspiring, and impactful for all of us. So thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Iqbal, for the insightful message and for highlighting the importance of collaboration in advancing mathematical research.
Proceed to our next agenda. We are honored to invite Professor Agus Muhammad Hatta, Vice Rector of Institut Teknologi 10 November, to also deliver the opening remark and opening the conference. To Professor Agus Muhammad Hatta, the stage is yours.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi dan salam sejahtera untuk kita semuanya. Very good morning, honorable invited and keynote speakers, honorable Dean of Faculty of Science and Data Analytics, Professor Dewi, and respected Head of Department, Prof. Didik Husnul Arif, and colleagues from Department of Mathematics at ITS, the ICoMPAC participants, the students, and all ladies and gentlemen. So it is a great honor to be here with you at the opening of this international conference on mathematics, pure, applied, and computation, ICoMPAC 2025. It is the 9th seminar, the 9th ICoMPAC, meaning that the next will be the 10th ICoMPAC. So I should appreciate the Department of Mathematics who held continuously this important seminar and conference. So congratulations to Department of Mathematics, ITS, for this important seminar and agenda. So, ladies and gentlemen, today also we have a remark on the 16th anniversary of the Department of Mathematics at ITS. For 60 years, this department has been an important place for learning and research in mathematics in Indonesia. I think more than 5,000 alumni, I suppose, that this department producing the mathematicians. Today, we celebrate its long and important history. So, ladies and gentlemen, I really appreciate the chair, Dr. Muhammad Iqbal, for this preparation. Thank you. And when I was asking to give an opening remark, I was thinking about what I have to say to all of you. And I remember my time during a PhD student. During those years, I love to read biographical books. So I found some interesting book, and I still remember the content of this book. It was very inspired, the book, and also the figures. So the book is about the life of mathematicians. Two people, two persons. I remember. The first one is Srinivasa Ramanujan, and the second one, Paul Erdos. Srinivasa Ramanujan, the book entitled "The Man Who Knows Infinity," if not mistaken. Ramanujan came from a simple background, but had an amazing feeling for numbers. He reminds us of the power of being very curious. He saw beauty in ideas and patterns that others did not see. His story shows us that one person with a lot of patience can discover a new world, and that even very theoretical work can become very useful one today. His works also very important in our computation today, the work for algorithm, the work of in numbers and also for computation today. The second one, there was a Paul Erdos, the book entitled "The One Who Loved Only Numbers," the book entitled. Paul Erdos is a mathematician who traveled the world with his suitcase. He traveled a lot during his time and he has no house, even the family. But he has a company, the mathematician all around the world. He believed in working together. For Erdos, maths was not something to do alone. It was something to do with other people. He taught us that the biggest problems are solved when many people work together, sharing ideas, asking questions, and helping each other. So, Ramanujan is like a fire, it's like a spark of a single great mind. And Erdos is like the spirit of teamwork that turned that spark into a big flame. Looking all participants today, I see both of these spirits, spirit of great mind and spirit of working together. And I believe these two spirits are really important even than before, even than the previous decade. Our conference theme is Mathematics and Computation for Sustainability. This theme asks us to do something important. The problems we are having today, like climate change, using our resource wisely, keeping our economy healthy, are very big and difficult. We need the new ideas of Ramanujan to find solution, and we need teamwork of an Erdos to make solution happen. Ladies and gentlemen, with the recent age, with the computer, we now have tools that Ramanujan and Erdos could not even imagine. We can study difficult problems, look at a lot of information, and find the best ways to do things for the world. So I believe this conference is our time to work together. It is our chance to connect, share what we have learned, and build new team to help create a better future. So today conference, I hope all of you do more than just listen. I encourage you to be like Erdos, meet new people, ask good questions, and start conversation that can lead to something great. I also encourage you to be like Ramanujan. Follow your ideas, try new things, and always stay curious. Ladies and gentlemen, today let's celebrate the 60 years of ITS Department of Mathematics. Congratulations, Pak Didik, and all colleagues at Mathematics Department, by making this conference for a teamwork and new ideas. Thank you, and I wish you all a wonderful and useful conference. Thank you very much. Billahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
We kindly invite Professor Didi, Dr. Dewi, and Dr. Iqbal come up to the stage to officially open the ceremony.
Number 9.
Thank you, Professor Agus Mohamedata. Your message truly inspires us to continue fostering research excellence and collaboration.
To continue the program, we are very delighted to present a special welcoming performance by Mathematics ITS student, Tari Saman. Ladies and gentlemen, please enjoy.
Assalamualaikum. Kamu ucapkan Jame banteka karena salam Nabi kesunah Jarota memang syarat mulia. Assalamualaikum kami ucapkan pada undangan yang baru teka karena salam Nabi ke sunnah jarota memat tanah mulia mulia wareh dan pelampuan mulia rakam rame suara karena salam Nabi ke sunnah jarota memat tanah mulia. Hai la ilallah ilallah he wasihone imalah he imalah matua la ilallah ilallah adanya serama makan matua pusaka kaya la ilallah ilallah he wasihone imalah he imalah matua la ilallah ilallah adanya serama makan matua pusaka kaya. Lalai lalai wasione lalai lalai betua lalai lalai lalai. Nafsi hujala jala, nafsi hujala jala, nafsi hujala jala, nafsi hujala jala, nafsi hujala jala. Borang kata karang dua, borang kata karang per, borang kata karang enam, dan bubuk sinan dalam, sinaru sinaru kipa, kipa kipa sinaru, sinaru sinaru kipa. Saborang kakarang dua, saborang kakarang per, saborang kakarang enam, sinan bubuk sinan dalam, sinaru sinaru kipa, kipa kipa sinaru, sinaru sinaru kipa. Amin Allah semua amin. Urek bukmin gela gela ke doa berkat rahmat Allah yang beri. Nanggro Aceh jadi makmur sejahtera. Amin. Allah semua amin. Surah amin. Lagi doa berkat rahmat Allah yang beri. Nanggro Aceh jadi makmur sejahtera. Lale ge tanyu lale. Anajan tate umuka tua. Utengon janggot kuningon bise. Antara jombet kamu salah. Utengon janggot kuningon bise. Antara jombet kamu salah. Antara jombet kamu salah. Antara jombet kamu salah. Lale ge tanyu lale. Anajan tate umuka tua. Utengon janggot kuningon bise. Antara jombet kamu salah. Janggot kuningon bise. Antara jombet kamu salah. Lale, 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 lale. Hai jalan tumile mile jalan tune jalan tumile mile jalan lambung kontak sayang non kawan lapa dalam pot angin gelebohan terbah melintasi jalan tumile mile jalan tune jalan tumile mile jalan lambung kontak sayang non kawan lapa dalam pot angin gelebohan terbah melintasi jalan tumile mile jalan tune jalan tumile mile jalan. Hotlah hotmananan, cok ampun sengkuraja. Singgung merah di lulang salaman. Hotlah hotmananan, cok ampun sengkuraja. Hai kutite bungkomai kutite, hai kutite mang payung kemang berhati. Kaduang donya puja ke Tuhan. Urang malam bisa gak lupa. Hai kutite bungkomai kutite, hai kutite mang payung kemang berhati. Hailah otsa, hailah lambat me, are kapai di etre mebura, hai bacut me, salah berkensah, lalang salama, lapen awai di gata perahu, hailah lambat me, are kapai di etre mebura, hai bacut me, salah berkensah, lalang salama. Lapan awai dua hala otlah helalah batna ada kapaji eta bura baca salah bekerja lalang selama lapan awai kata helah batna ada kapaji eta bura baca salah bekerja lalang selama lapan awai alam. Tinjala he, tindikala haidi, kojala hala. Tinjala he, tindikala haidi, kojala hala. Tinjala he, tindikala haidi, kojala hala. Tinjala he, tindikala haidi, kojala hala.
What a stunning performance. Let's give another round of applause for the talented dancers.
To commemorate this wonderful gathering, we invite everyone to have a group photo session in front of the stage. Please follow the direction of the committee to arrange yourselves in front of the stage. We kindly invite everyone to have a group photo session in front of the stage. So please, to every participants to come up to the stage to take a photo.
Ladies and gentlemen, before we proceed to our main agenda, will we have a short coffee break?
Before we move on, we would like to mention that this program is sponsored by Prawatya Karsa Pradipta, Jagat Sanitasi Indonesia, Adiluhung Sarana Segara Indonesia, Telkom Indonesia, and boring AI.
Thank you once again to our sponsor for the generous support and to everyone joining us today.
Ladies and gentlemen, the refreshments are available right outside the ballroom, so please feel free to enjoy a cup of coffee or tea, and we will reconvene shortly at 9 a.m. for the keynote sessions. To all participants of the conference, please come back to the ballroom for the keynote sessions.
Ladies and gentlemen, please come back to the ballroom for next agenda. You can bring your food or coffee inside.
Even you can walk around.
Who will tell me to show the slides? Next one. No, maybe I can just.
Ladies and gentlemen, please come back to the ballroom for the next agenda.
Should I set the timer?
Ladies and gentlemen, we please ask you to come back to the ballroom for our next agenda. You may bring any food or beverage.
Ladies and gentlemen, now that we all had our moment to refresh and recharge, we finally arrived at the heart of today's conference. This session is a series of keynote and paper presentations that will bring forward fresh perspectives, new methods, and meaningful discussions. We will have keynote presentations and followed with Q&A discussion that will be moderated by Dr. Muhammad Lutfi Shahab.
It is my pleasure to introduce our keynote speaker session of the day. Firstly, we will have Professor Hongxi Liu, who will present insight on AI security.
Professor Tsuyoshi Miyazaki, who will discuss advances in material science.
Associate Professor Dr. Rino Morti, presenting her research on graph theory.
And Professor Agus Hassan, joining us virtually to share his work on digital twin technology.
To our moderator, Dr. Lufti Sahab, and our keynote speaker, the stage is yours.
Assalamu alaikum warahmatullahi wabarakatuh. Good morning, everyone, and welcome to this keynote session of the ICoMPAC 2025. My name is Muhammad Lutfi Shahab, and I'm honored to serve you as your moderator for this hybrid session. We are delighted to have both on-site participants here in the hall and online participants joining us via the conference platform. We truly appreciate your presence and participation. Today we have 4 distinguished keynote speakers. Each will have 30 minutes for presentation, followed by around 15 minutes for questions and discussion. For those attending on site, please make sure your mobile phones are on silent mode. We kindly ask everyone attending online to keep their microphones muted during the talks, and please use the chat box to send your questions during the talk. Let us begin with our first keynote speaker. It is my great pleasure to introduce Professor Liu from the National Taiwan University of Science and Technology, Taiwan. So this is the CV from Professor Liu. And the title of his talk is AI Service Platform with ORAN Toward AI RAN. Professor Liu, the stage is yours.
Thank you, ladies and gentlemen. It's my great honor to invite it as a keynote speaker here. So today, actually, I just want to share some experience about constructing AI service platform with ORAN and toward AI RAN. This topic is just about my project. And we are so proud that we are selected as one of 5 big projects supported by Taiwan government about 6G construction. So actually, I'm the professor in ECE of NTSC. At the same time, I also work as a dean for the College of Electrical Engineering and Computer Science. So okay, next one. It seems that, okay. So maybe before, I'm not so sure that if any problem with my files. So before my formal introduction to the topic, I'd like to use this map to show how strongly connected between my lab and Indonesia. So I believe you know this map is about Indonesia, right? So in total, right now I have around 30 more students from Indonesia, especially I have 6 students from ITS. So you can see from Sumatra, Java, and even the Kalimantan, I have students just from there, okay? So next. So let's just get back to the topic I want to share with you today. Then today, maybe I just divide it into several sections. As I know, I just have 30 minutes. But since, as I told you, that right now we are just in 5G stage. So in the beginning, I want to share you some concept about 6G vision, AI RAN, and the O-RAN. Then AI play a very important role in the coming mobile networks. So AI ML platform is very important. So I also want to share you some experience about how to construct a AI ML platform. So, and I also demonstrate some achievement right now we have. And then I will read up some key points for the conclusion. So next. Okay. Okay, maybe we just direct go to next slide. Okay, so you can just see the evolution about mobile communications. So I'm not sure if anyone here, you just use the handset for 4G. Do you? 4G, 1G. Do you? Oh, really? Okay. Maybe it's just relieve your age. Okay. So at that time, you know, the smartphone is very big. Only 2 types of person can just hold a handphone. One is the very rich person, right? The second one is the gangster leader, can both, you know? So it's so big, just like this one, and very heavy, just like brick. So during the negotiation, sometimes it can become a weapon. You can just hit your competitor, right? So at that time, the smartphone is very, very big, but it also shows your social level. I believe you can understand this. But as the time goes by, the smartphone become smaller, and smaller. So right now, I believe maybe you hold 2 smartphones or even more smartphones at hand. So starting from 6G, in each generation, there are some key features for different generations. Like for 3G, we have WCDMA. And then 4G, we start to focus on FDM, MIMO, okay? Then 5G, right now, we are just in the 5G era, right? So we focus on like a millimeter wave and URLC and massive MIMO technology. But as for 6G, actually, everyone, we just, you know, like coverage, we just enlarge the coverage from large to extreme large. For the speed, we just from fast, and then become extreme fast. But people always believe that AI can do something for the coming generation of mobile communications. So in the future, AI will play a very important role in the 6G communications. So like 6G, maybe we need to face the it should be very cloud native and AI native. Okay, so please go next. So in the beginning, AI can help with the RAN aspect. So why is the RAN? Because maybe most of you come from different fields, so you may not have the background in telecommunications. So I want to show you some basic terms. The first term is RAN. RAN means radio access networks. So you can just regard RAN as a, so you just hold a phone, right? You can access the internet. But there is something helping you to connect the internet. So that's RAN, radio access network. So you can see for the left-hand side is the user equipment, like your phone. Then the right-hand side is the internet. We call it core network. So in between, we have RAN networks to bridge user equipment to core networks. So there are some like base stations, control systems for mobile systems. Okay, next one. So actually, AI helped to develop the mobile communication networks is not the first time because, you know, even for 3GPP, 3GPP is the organization to define the standards for the mobile communications. So actually, 3GPP also proposed that AI can help to improve the channel estimation and also the beam management and also position accuracy. So you can see these three terms are very important for network management, especially for the mobile network system management. Can we go to next? So right now, people just think that can we just add the AI element into the RAN element? So you can see for your left-hand side, you can see in the past, RAN may be just related to the base station. So we will just embed RAN baseband unit into the base station. And all control will be the core network side, like cloud side. But right now, we try to add the AI into the RAN. So you can see for the right-hand side, not just about the application will be added with AI, but also we just add AI into the RAN control. So you can see for the right-hand side, we just move AI into the RAN control part. So next one. So right now we have a AI RAN Alliance. They just proposed 3 working groups. The first one is AI for RAN. And the second one is AI and the RAN. The final term is AI on RAN. So for AI for RAN, it's quite intuitive because you can see there are so many control and management mechanisms in the RAN part. So why not we just use AI to improve the performance for RAN? So this part is for AI for RAN. But as for AI and RAN, AI, you know, AI right now, we just mostly apply for AI to different application fields. So if AI, because we know if you want to run AI algorithm very smoothly and very efficiently, you should have enough computation power, right? So in the future, the RAN will be very, very software-based. Later I will show you this part. Then if the infrastructure can be constructed by the computer system, why not we just leverage the same resource for AI computation? So let's say it's for AI and the RAN. And the last part is AI on RAN. AI on RAN means that, you know, RAN will be able to control some application. So for different application, I also will share you some application for this part. For different application, the response time will be different. Like if you just use to control the unmanned vehicle, you need to make a decision within many minutes, right? But if you want to just change the network management strategy, maybe every day, you just change it one time, it's more than enough. But for some application with a very real-time demand, you need to make it very make the decision very efficiently and very quickly. So next one, next slide. Okay, so to achieve this goal, Open RAN just was proposed. Of course, Open RAN is not a new term for 6G. Actually, Open RAN is already was developed in 5G right now, but maybe it's still not that popular because Open RAN means it's open for. I believe most of you just know the software development, right? So we know open source. So in the past, because I also work in tele company for years. In the past, if you want to construct the infrastructure for providing the mobile system, you need to buy the equipment from like Siemens, Nokia, Ericsson. So after you buy their equipment, one day if you want to replace some parts, or if you want to replace some key components, you need to go back to the original vendor to buy the equipment. So normally the equipment is very, very expensive. So if we go for Open RAN, that means that we just divide the RAN into several components which are very, very software based. Then that means that we can just easily buy some computer and install some software to provide the same functions for communications. So you can see, take a look at this picture. At the left-hand side, it's a traditional RAN system. So from very top level, we have some control, and for the very low level, we will have RF control. But we just disaggregate these elements into several parts, like CU, DU, and RU. These ones are communication units, which are based on software. So that means if you want to change some function, you can just change the software module. You don't need to buy the new parts from the vendor. So even for, like we are software developer, right? For us, it's a good time to get involved in the development of mobile communications. So it's really a good change. Let me just take another example to you that, for example, I believe you are a computer user, right? I believe at your home you have computer. But one day, if you just run out of your memory, what's your next step? You just go to the computer store to buy more RAM, right? When you buy the RAM, did you care about the RAM is coming from Korea or from US? You don't need to care about that, right? So that means RAM you can buy from company A, but the CPU comes from company B. Then hard disk coming from company C. So that means that we can just make the cost of constructing the mobile system become lower. So that's the main purpose for Open RAN. Okay, so let's just go next stage. So based on this concept, we have different applications that will request different response time. Like, for example, if we want to control the mobile devices like an unmanned vehicle, maybe the time will be very restricted to like millisecond level, right? So you can see if you want to control a car, turn left, turn right, the decision cannot be too long, right? So normally you need to make the final decision within several minutes. But if you want to like change the network management strategy, like parsing, modeling, and slicing, maybe you can tolerate more than 1 second. Even one day you can just make it one time. So you can see different demand. They will serve different scale of the devices. Okay, so you can see from very real time to very non-real time. Next one. So based on the introduction about the background, you can see AI must play some role to support these conditions. So in this project, we mainly focus on how can we just build an AI ML platform with ML ops capabilities to support such a demand. So next one. So this figure just showed a traditional way to how can we just proceed the AI ML model from training, from data collection, model training and inferencing, then go back to retrain the model again. Next one. So in the past, you can see the process, the procedure is kind of fragmented. So can we just streamline the workflows from the left-hand side, which is very fragmented, then to a very integrated. So we just streamline the modules, like we just put data processing, training, and fine-tuning into the AI ML training system. It's a subsystem. Then can we just separate the rest part like deployment, inferencing, and monitoring as the second part for AI ML deployment system? So we just separate it. We just let the system become not so fragmented. And then, next one. And we also follow the ML ops. ML ops means machine learning operations. They will follow these 4 stages. The first stage is development, including data preparing, model training, and then try to integrate these components by some pipeline. Then after we just have the model, we just deploy this model. Then we need to monitor the performance of this model, right? So after we monitor that and achieve some threshold, we need to retrain the model. So the loop should be carried out again. Development, integration, development, then deployment, and then monitoring, okay? And then we just continue the loop. So we can have the next. So we just have a simple comparison. If the AI ML platform with or without ML ops, what difference will be produced? So without ML platform or ML ops, maybe the efficiency is poor, and the scalability is low, and the reliability also low. So with the help from the ML ops, we can just achieve high efficiency, high scalability, and also high reliability. Okay, so next one. So I just introduced the concept about AI ML platform with you. Then right now I want to show you what we have done for this platform. So we practically implement such kind of system, I mean for the AI ML platform. So from very top level, we have a training platform. Normally, we just put this part into the cloud side, like Google, AWS, okay? Then we also develop our AI ML platform in our lab. So we just carry out model deployment and result collecting and inferencing monitoring. Then finally, we must deploy some inference node. This part just help make the decision for different kind of applications. And besides, in between, we have a messaging system to bridge. So you can see for the left-hand side, this is a training platform. For the right-hand side, this is a deployment platform. So we just build a messaging system in between to deliver some message between these 2 subsystems. For example, after the model has been trained well, then we will notify the deployment platform that, okay, the model is well trained here. Please just deploy the new model. And by the way, if the model goes in a very efficient way, then it's time for us to retrain the model. So we need to notice the training subsystem. Please just retrain the model again. So we just use the messaging system to bridge these two subsystems. Okay, next one. So this slide just show what we have achieved right now. So I just take some snapshot for your reference. Like we have some pipeline. Actually, this is our web pages. So we can quickly go through this one. So this one is for data processing, training, deployment, and display the train model. Next one. So this is also another one. And then you can notice that for the right-hand side, you can see our system will keep watching or keep monitoring our system. So once the performance is not that good, then we will activate the retraining again. So it's just look like a loop. Okay? Next one. So I also show you some evaluation and application demonstration. The first one I want to show you is about the total time. So with the messaging system help, then you can see that the total time can be kept almost constant. But if you just follow the traditional way, this is for the blue part, you can see as the number of applications increase, you can see the response time, the total time will also increase. Next one. So this part is try to evaluate the package success rate. So you can see as the number of application increase, if you just use our solution, you can see the success rate can still keep very high, even near 100%. But if you just follow the traditional way, I mean the blue part, you can see as the number of the application increase, the package success rate also decayed. Okay, next one. And before the end of this talk, I will also show you some demonstration. We practically construct the system from the very top level, and we also add our AI platform there. Then we build the system here. You can see there's a snapshot for our system or for our component for the whole demonstration. So next one, I have a short video to show our system. Okay. So we just demonstrate how we integrate our platform with some application. And my Indonesian student just focused on the smart agriculture. So you just imagine that the drone is flying in some farm. Then once the drone just go into an area with a very weak signal coverage, then can we just try to indicate try to enhance the coverage? So you can see, you can just imagine that the smartphone like the drone is continuously moving, right? So can we just integrate the rays to enhance the whole coverage? So actually this is our system about the digital twin by following with the help from the tracking system. So due to a time constraint, maybe we can skip this part. Okay, so I just want to wrap up some key points about my talk today. And you know, in the beginning, I just showed you some history about the mobile communications, right? So evolution from 5G to 6G, we definitely need to adapt the concept about AI and also cloud solution. Then the AI RAN just transfer RAN from a connectivity provider to an intelligent coverage compute and communication platform. So that means in the past, RAN just play a bridge to connect your equipment to the core networks. But right now, the RAN part will become more intelligent and much smarter than before. Okay? Then O-RAN also provide a very key component to enable AI RAN concept. Especially we are working in academia, right? So O-RAN is open, so everyone can get involved with the development for RAN. So it's our opportunity, right? And I also show you the AI ML platform we built with ML apps capabilities. So with that, we can just evolutionize from a very fragmented AI workflow to integrated workflow. Then as for the architecture, I just show you that we just integrate training, deployment, machine, mechanics together. And finally, I just demonstrate smart farming with the ORAN and AI ML platform helps. So that's my presentation today. Thank you everyone.
Thank you very much, Professor Liu, for that insightful and inspiring presentation. We now have about 10 minutes for questions and discussions. We will begin with questions from the on-site audience, and then we will take other questions if there are other questions from our online participants. If you are here in the hall and have a question, please raise your hand, and please come closer to the camera, in front of this camera, so our online friends can see you too. For those joining online, please type your questions in the chat box or use the raise hand feature, and we will invite you to unmute. Any questions or comments from the audience in the hall? Yes, please, maybe. This one. Okay. Could you please stand in front of the camera so our online participants can see you?
So, hello everyone. My name is Himanshu Tiwari. I am from NTUSD. So, Professor, I have a very curiosity. So, I had few questions. So, like, which area in AI RAN research are most often for academic collaboration at this moment in which we can work? And is there any available source where we can do the experiment on AI-driven networks? So, these are the two questions which I have.
So your first question is about, can you just repeat your question?
So at this moment, is there any open area in this particular category in which we can collaborate?
Okay.
And what are the available resources or simulation tools which we can use?
Okay.
Thank you.
So as I told you that actually we just adapt the ORAN solution. Yeah. So open RAN means it's very open. So that means everyone, the applications or the source codes are available. So you can just get involved. So I just share you one fact that my students just continue to contribute something back to the OSC. It's also an institute focusing on how to use the open source to carry out the communications features. So that as I told you that here right now, actually, due to the time constraint, I cannot introduce the detail to you. As for the, there are so many components like CU, DU, and CU, DU, and RU. Then in the ORAN system, it will become OCU, ODU, and ORU. All means open. Yeah. So in the academia area, we can just, we can just use the source as your basis, then develop something and contribute back to the organization. And as for cross different universities, because, just like in Taiwan, right now we are in 5G stage, even beyond 5G. Right now we have
beyond 5G, exactly.
Private 5G, right?
Yes.
But we believe 6G will be the next step. But in Indonesia, maybe you have different culture, you have a different user behavior. We can just exchange opinion with the professor here or the researcher here. So we can just, for example, we can share our experience with you. But because you have your population is much higher than Taiwan, so the problem you encounter may be different. So you can share the experience with us. So how can we just solve the same problem? So yes. I believe that will be a good collaboration model. Yeah, just for your reference.
Thank you, Professor.
I hope I can answer your question.
Yeah, and one thing, so usually when we talk about networks,
yeah.
we have different frequencies.
Yes.
And so when I say that we are doing a test simulation, So these frequencies always be the free frequencies or the frequencies for which we require licenses?
Maybe different governments will just have different regulation, right?
Exactly.
So the regulation will just constrain you to use different frequency. But of course, in the beginning, you must simulate. You should just need to conduct some simulation in your PC.
Exactly.
Then you need to, with the agreement from your government, you can use the free the spectrum is for free for development for scientists for mechanical. So you can just follow the stage to gradually realize your idea.
Thank you, Professor. Thank you so much.
So you are from NTUST?
Yes, I'm
Okay.
from ITST.
Which department?
Computer science under Professor Binayak.
Oh, okay.
Thank you.
Computer science.
Yes.
Thank you for your questions. So we have another question from Padika. Yes.
Check. Okay. Thank you very much. So my name is Tika from ITS. So I actually have a question, and actually you from the previous question you mentioned about the frequency,
Yeah.
and when in 5G we have 2.4 gigahertz and 5 gigahertz, which as we know, the 5 gigahertz one is less stable than the 2.4 one, and for the 6G, I'm really interested whether from the topic that you have discussed before, is it going to be more stable or more stable, and how can this ORAN and AI-RAN ensure that? Maybe that's the question. Thank you.
Okay. So as for the spectrum, as the frequency goes higher, actually the stability is a big challenge. Yeah. So because I don't have enough time to introduce our project, actually our project also get involved in using the optical free space communication. So just like you enter the room, actually optical can help. Not just rely on the traditional radio. Yeah. You can just use the optical communication, free space, to help you to improve the communication quality. Otherwise, if you go outside, if the frequency goes so high, actually it's not workable. So we must, in the future, it must be a heterogeneous net. If you stay in different places, maybe different technology will help you to provide the most suitable environment to you, something like that.
Exactly. Yeah.
Okay.
Thank you.
Welcome.
Are there other questions from the participants in this hall? Yes, please. Maybe this will be the last question for this session.
Hello, Professor. Thank you for an amazing explanation about 6G. Actually, I was reading about 6G and its implications and how it's going to operate in the field, and I was reading that it will be a life changer, not for simple and normal internet users like us, but for surgeries and construction equipments, because you can operate remotely and you can do perhaps like the surgery and also the cars. Do you see other implementations or where we can see also these 6G networks like taking part of our lives?
Yeah. So actually, sometimes people also challenge that is there any difference between the application? I'm talking about the application. Is there any difference between 5G and 6G? Sometimes maybe it's not. We don't have too much difference. But as I told you, as I explained earlier, that as in the 6G, actually we still need to rely on the satellite. So we need to provide more technology to make the coverage larger than before. So when you just talk about application, actually they are almost the same. But due to, as I told you, the coverage will keep increasing. So in your mind, you can just bravely think about more applications like surgery. Surgery in the past maybe is workable in the indoor environment, but do you think about if at the mountainside? without satellite, I'm afraid you cannot just conduct the same function as you mentioned earlier. So in the future, maybe the application, we don't have too much difference. However, since the coverage become better, so you can just carry out the same application in different environments. Like in the past, maybe you cannot, maybe you will challenge that no medical doctor will conduct surgery in the mountainside, but it's hard to say, right? Sometimes if you have some emergency call in the mountainside, and then you need to do that with the 6G help, then maybe it becomes possible.
All right. Thank you.
Like
Thank you very much,
okay.
Professor.
Thanks for your question.
Yeah. Thank you very much.
Thank you very much for all the participants who have the questions. We don't have any question from the online participants. So thank you, Professor Liu, for your answers and valuable insights. Please join me in giving a round of applause to Professor Liu.
Thank you, everyone.
Thank you once again, Professor Liu. We will now continue with our second keynote presentation. I would like to invite Professor Miyazaki to come up to the stage. So this is the CV of Professor Miyazaki. So Professor Miyazaki is a researcher in computational materials science. And the title of his talk is Large-Scale DFT Study of Complex Nanoscale Materials Using Conquest. Professor Miyazaki, the stage is yours.
Thank you very much for the introduction. And first of all, I would like to thank the organizers for inviting me to this wonderful conference. Actually, it is the first time for me to be in Indonesia, and all of them are just really new, and I'm really enjoying my stay. So thank you very much. So today, I would like to talk about, I'm doing the computational material science, and I just want to explain some overview of the computational material science and what kind of computations we are doing, just to overcome some problems we have. So I'm from National Institute for Material Science in Tsukuba in Japan, and I also belong to the Research Center for Materials Nanoarchitectonics. So my work is related to the nanotechnology. Next, please. So this is the outline of my talk today. So first, to be honest, I thought most of them know the density functional theory calculations, because in my field, it's really, really well known, and it's very important for the materials research. But this conference is for the mathematics. So I just want to explain briefly about the materials research. I just want to talk about DFT calculations and what kind of computations we are doing. Then the second part is our activity. And because DFT calculations has some problem for the size problem. So if we want to work on the really complicated systems, we have some limitations. So to overcome this limitation, we have been developing our code. This is some international development, and I will talk mainly about this second part. Then I will summarize my talk. Next, please. So first, just introduction. As I said, I'm doing the computational materials research using the DFT calculations. And for this, first, for this computational materials research, what I just want to say first is we perform electronic structure calculations. It's because that the property of materials are determined by electrons. So properties like the electronic transport property or magnetic property or optical or optoelectronic property or the chemical reactivity and also the mechanical or the thermal property. All of these properties are basically determined by the materials are basically determined by electrons. And in our calculations, for the total energy or the atomic forces are obtained by the electronic structure calculations. And for the electron structures, the behavior of the electrons is governed by the quantum mechanics. So we need some quantum mechanic simulations. So for the materials research. Next one. And what we are doing is called the first principles calculations based on the density functional theory. And this, as I said, this is based on the quantum mechanics, and it's not the classical molecular dynamics simulations. And what we are doing is different from the finite element method type calculation or model calculations or phenomenological simulations. What we are doing is we employed some atomistic simulations to study the property of materials. And our target is all materials, basically, all kinds of materials. So, for example, the metals or insulators or semiconductors or oxides, or the molecules or clusters or biological systems, or the surface, interface, liquid defects. All of the materials are our targets for the DFT calculations. And for the, to work on this kind of things, useful, we need an ability to predict properties of known or unknown materials quantitatively. And actually, this DFT calculation, density functional theory calculations, has an ability to do that. And our calculations are reliable and accurate, even without experimental results. So, because of this ability, we can calculate the properties of the materials under extreme conditions, like high temperature or the high pressure, where the experimental information is very difficult to get. But still, we can provide useful information for the, in such cases. And also with the recent advance of the data science techniques or the AI type calculations, with this DFT ability, we can also design the new materials, which is not discovered yet. And there are already some examples, to find some new batteries, or the good performance of the battery, or this kind of things is already appeared. So this is really, really DFT, the DFT calculations are really, really efficient or powerful. Next one, please. Yeah, so I just wanted to show that what kind of computations we are just doing. So I put several equations. So let me just try to explain. So in this DFT calculations, density function theory, the total energy of a system is a functional of the electronic charge density. And the charge density is the sum of the occupied Kohn-Sham orbitals. Kohn-Sham orbitals is the wave functions, so like the quantum mechanics. And to optimize the total energy with respect to the wave functions, we can get this third one, HDFT psi nu equilibrium. So we have the equation called Kohn-Sham equations, which is similar to the Schrödinger equation in the quantum mechanics. And what we are doing is we need to solve this for this Kohn-Sham equation to get this wave functions. And for this, because to solve this, we use the basis functions, and we expand the Kohn-Sham wave function using the basis function. Then this Kohn-Sham equation becomes so we can calculate the Hamiltonian matrix using this definition of the Hamiltonian. And what we need to do, we mainly need to do is the diagonalization of the matrices. So that's what the main computation part in our calculations. Next, please. So again, this is the computational flow of our calculations. And the input data, in our case, is just the atomic positions and atomic species. Then we'll get the initial charge density, then Hamiltonian, and we need to do that central part, is that we need to do the diagonalization of the Hamiltonian matrix. then we can get the outside output charge density, and we do it. We iterated this calculation until the output charge density becomes the input charge density. And then after that, doing this type of calculation, we can get atomic forces. And from these atomic forces, we can calculate we can perform the structure optimization or the molecular dynamics simulation, or we can also calculate a phonon property. So the property of materials can be calculated from that. And we also have the wave function and its energy. And from that, we can calculate the transport properties, electronic transport properties, magnetic properties, and also optical properties. So these are really powerful methods. Next one, please. So as I said, the DFT calculations are very powerful, but very expensive, especially for the large system. And it is because that the cost of the usual DFT methods increase very quickly when the number of atoms n in the target systems becomes large. It's because that the size of this Hamiltonian matrix is proportional to the number of atoms. So as I have shown here, the cost is proportional to alpha n cube. So it means that so there are many commercial, free and commercial DFT codes, the programs to do the DFT calculations, because all of the computational physicists using this DFT method. But still the typical size of our DFT calculations is usually a few hundred atoms. So, and it is very expensive, the treated systems, when the number of atoms is over 1,000. So it's our problem. So it means that, so the left one is, this is some metallic catalyst, the catalyst system. And the left one is the typical size of our DFT calculations. But if we want to do the more reliable and more, we want to, sometimes we want to consider the effect of the steps or these kind of things. And if we want to do this right system, it increases the 8,000 atoms, so 50 times larger. Then because of this poor scaling, the computational time is proportional, 125,000 times more expensive. So it's almost impossible, using the usual DFT methods. So this is the problem of our field. So next one, please. But in our case, in the many cases now, we need to treat many complex systems, like the semiconductor surface, or the nanomaterials, or the nanowires, or the nanometallic catalysts. These are really, all of them are very new and brand new systems, which we need to do, and also for the DNA systems. And for this kind of things, we often need to treat very large systems containing more than 10,000 atoms. But as I said, using the usual DFT programs, it's just impossible to do this kind of type of calculations. So next, please. So to overcome this problem in our community, we have been developing this large-scale and linear scaling DFT code called Conquest, and it's jointly developed by our NIMS team and UCL in the UK and also in the Bordeaux. And with this method, with this code, when we also introduce the method called order in the method, and in this case, both CPU time and memory requirements are only proportional to n. So the method is suitable for large systems. Next, please. So I just want to show the development team of the of this, our conquest code. And these are the key person. And we also have the students and postdoc researchers working on this code. Next one, please. Sorry, this is the overview of the code. And I'm sorry, I don't know how many people are doing actual DFT calculations in this audience. But there are, as I said, there are so many researchers working on the density function theory. And our code is basically using the standard DFT methods so that we can also compare our results with the usual standard DFT calculations. But the big advantage of our code is we introduced some, in this sense, the mathematical techniques. And by introducing this kind of things, mathematical techniques, we can overcome this size problem, our problem in our community. And I just want to explain briefly about, we have two methods, which the first one is called multi-site support function method. This is just reduce the factor alpha one. And the second one is called order n linear scaling method. So we just change a revised method has the different scaling. So I just want to introduce these two methods. And it's also important for us that because we are aiming for the large-scale DFT, large-scale calculations, the massively parallel efficiency is also important for us. Okay, next please. So this is the first one. I don't go into details, but the key idea, this is called multi-site sample function method, is that by calculating the local electric structure, we can reduce the number of basis functions. So we can reduce the size of the Hamiltonian matrices. Then the total, we still use the diagonalization for this case, but as we can reduce the number, the dimension of the Hamiltonian matrices, we can expect the calculation cost, the reduction of the calculation cost with this order. And the first method is really good that this method can be used for all of materials. So it's very robust. And we can use this method for any materials. Next one, please. And with this method, this is the example of the calculation. And this is the graphene on the lodging metallic surfaces. And so for this, if we use the standard method, we need the number of nodes is 72 nodes. And but still, it's possible to do the calculation, but with this 37,000 seconds, to calculate that. So, but with this new method, if we introduce, some new technique, even with the half number of nodes, we can reduce the CPU cost for the 66 times faster. So it's very important to introduce some this kind of techniques. The next one, please. The another method is called order n calculations, and this just revises the scaling itself. And in this case, we don't do the diagonalization of the Hamiltonian matrix, and instead of doing this diagonalization, we calculate the quantity called density matrix, which is defined as a sum of the wave functions. And if we introduce this method, we can optimize the density matrix to minimize the total energy. And we also use the locality of the density matrix. This is coming from the physics theory. And if this can be used, and this method can be used only for the semiconductors or the insulators in these gapped systems, But if we can introduce this method, we can do really, really powerful calculations, efficient calculation with this method. Next one, please. Then this is the really old data, to be honest. We have got this information, this data almost 13 years ago, 14 years ago. I mean, using the world's fastest computer at that time, called ICoMPAC. And here, this graph shows the horizontal line shows the number of atoms, and the vertical axis shows the actual wall clock time. Okay. And for this, I mean, we can see that this graph shows the so-called weak parallel scaling measurement. And you can see that so for each line shows the CPU time when the atoms per core is constant. And we can see that the CPU time, I mean, this line is almost flat. And it means that our calculation has almost ideal parallel efficiency, even with using the 25,000 nodes. It means that almost million cores. But still, our calculations was really efficient. And also, the graph shows that we already reached the 1 million atom system DFT calculations. As I said, with the usual DFT calculation in our community, the 1,000 atom is probably the limitation for the maximum number. But with this code, we already reached 1 million atom systems just by introducing some mathematical computational techniques. So it's one of the world's largest calculations. And still we have, I mean, this that's one of the world's largest DFT calculations in the world. Okay, so next one, please. And we recently released the code, and so with the MIT license, so everyone can use it. And there are many things, requests, to use our code. Next one, please. And we also have many collaborations. Because of our new technique, we have many collaborations in the world, and also for the development part, the left one, and also for the application part. And since we can do the DFT calculation, which they cannot do outside of our group, so many people came here. And for the application, we have some international collaborations. So many students, for example, came to our group and stayed for 6 months, then doing this type of calculations. Okay, so next one. I just wanted to show the research examples by conquest, but probably I don't have time to do it. So just roughly, let me just explain it briefly. Next one, please. The first system is this nano 3D. So this is based, again, related to the quantum dots. And the formation of the quantum dots, or how to control the size, or how to control the growth of this island is important. And again, as you can see, that the number to reproduce this system by the atoms is just impossible for the usual DFT calculations. But because we have the code, we can work on such really complex and large-scale systems. So next one, please. Another one is the collaboration with the experimental groups in our institute. And this is called the nanowires, the core shell nanowires. And this is the good candidate for the next generation devices, and which we expect that this system has a really good performance, the device performance. And but the size, again, the size is important. And in the experiments, they can control the size. So in collaboration with such experiments, we can design the next generation devices. Okay, thanks. And we also calculate the atomic positions, how to distribute the atomic positions, or we can also calculate the electron structure. And from this electron structure, we can predict the behavior of the electrons or the holes of the semiconductors of this really special nanowires by the calculations. And we can provide this kind of information to the experimental group, and we can develop the next generation devices. Next one, please. And we also did, to get the stability of these materials, we have done some, could you just type? These are the movies of the molecular dynamics simulation to check the stability of the, push again, please. And for the higher temperature, we can see that how this system can be destroyed by this guy, silicon, germanium, and hydrogen. Yeah, sorry, I cannot go into details today. So this is second examples. So without the experimental data, we can just get this kind of information just from the calculations. Okay, then next one, please. Next one, please. Okay, so the third one is the catalysts. It's a really efficient catalyst. So I just thought that this is related to the sustainability of the future targets. And it's really important to have an efficient the catalysts and with the really limited number. And this is the third example. And again, usual DFT calculations cannot treat this size system with the metallic nanoclusters on the support, we called. It's supported by some oxides. Okay, next, please. And yes, next, please. And for the other applications, we have many systems, and including in our group, and also for the collaboration with other groups. So there are many applications, and now we hope that we can increase the number of users by this using our code. Okay, so next one, please. Yep. Since the time is limited, I will skip that part. But recently, because in our case, we can treat really large and complex systems, so we can calculate the atomic structure or the electronic structure. But nowadays, it becomes more and more important to understand what we can get. So what we can get, what we have obtained by the DFT, our conquest calculations, becomes more and more complex, and close to the real systems. But to understand this part becomes more and more difficult. I will finish that. Then, could you just go to the next page? We need to understand the structure, what we can get, what we obtained. And for this, we recently used some AI type calculation or data science technique. So we keep developing some new method to analyze more complex data. In this case, the data is obtained from our large-scale DFT calculations. So for the students, actually this is in the collaboration with the AI Center in Tsukuba University, and we need several, new mathematical techniques, to analyze these kind of things, very complicated data. So I just want some new students or the new young researchers interested in to analyze this kind of things. Could you just go to the, yes, next page, sorry. I just want to keep descriptor, the dimensional method compared with other method. Our method is, and we can also analyze from the transition from the crystalline, liquid, or the amorphous forming part using this AI or data science technique. Then, to be honest, I just wanted to do quick calculation. No, going back, please. Just going back. Yes. So this is the summary of my talk. So first, I just wanted to say that the DFT calculations are powerful in the research of materials. And I mean, the material scientists already, all of the material science basically knows these things, but very expensive. And because of this, the expensive cost, and we have the problem of the size. And to overcome this size problem, we have been developing the large scale and linear scaling DFT code Conquest by ourselves. And the code is open with the MIT license. And because by introducing some new techniques, we have already overcome this size limitation of the DFT calculations. And we can reach, I mean, with the order n method, we already reached 1 million atom systems. And as I said, I mean, usual DFT calculation is difficult, I mean, to the three systems over 1,000. So, yeah, so that's what I wanted to say. And for the last part, I have skipped, but the analysis of local structure. So we need some, again, the new techniques just to understand what we have got. And we have many, many complex data. And to analyze this data, we need some new techniques, and we need some new researchers to be involved to enter this field. So that's my message from my talk. Thank you very much for your attention.
Thank you very much, Professor Miyazaki, for that insightful and inspiring presentations. We now have around 13 minutes for questions and discussions. Is there any questions from the, okay, please, one, okay. Yes, please.
From here? Okay, hi, Professor Miyazaki. So actually I work with efficient machine learning models, actually Gen AI models for edge devices. So like microcontrollers, but that is like microcontrollers. So, oh, sorry, could you hear now? Okay, so I generally work with efficient ML models or Gen AI models for edge devices like your microcontrollers to actually reduce the energy cost for green AI. Now, you actually said that these large-scale DFTs and this, I'm pretty sure they require high-order matrix multiplications, right? And they generally demand like high amounts of computational powers as well. So I'm pretty sure you're running these on GPU servers. So now my question was, is there any way, like, because you are working with material science, so rather than relying on something like, instead of GPU servers, because I work with the software part, have you ever worked with something like creating a different kind of material or something like that, which will instead reduce these energy costs? Because instead of focusing on the software part, but you rather focus on the hardware part.
So when you say energy cost,
yeah.
What is the?
So the energy cost will be because you're running so many complex equations and stuff like that. So I'm pretty sure you require large amounts of CPU or GPU time.
Yes,
so I'm pretty sure your energy cost will be high as well. So that is my question. So instead of focusing on the software, have you focused on something like creating a better hardware source like that?
So for hardware, to be honest, we have some attempt to do the calculation with GPU, but at present, we don't use GPU machines so much. But still, I mean, usually GPU machines and the parallel calculations. I mean, in Japan, the fastest computer at present is Fugaku. I don't know which used to be the fastest, but in the world, but I don't know the present ranking. But anyway, Fugaku is not a GPU machine. Yeah. Okay, so the parallel efficiency is more important, so far, for us. Okay. And in this sense, the communication for the network and the reduction of the computation is our main task, used to be our main task. And Yeah, is it okay?
Yeah, I'm understanding,
Yeah.
yes.
And for the reduction of the computation, we introduced some new techniques, as I just explained.
Yeah.
And in addition to this, we also make the code very local. I mean, dividing into the several parts. And also the communication with the other, the neighboring part. Okay. We reduce, this kind of network. And to be honest, it's a really difficult part for the quantum mechanics calculations because usually all of them are just interference in the quantum material calculation. But again, introducing some technique, we achieved this kind of locality in the method and in the code.
Okay.
So we use, this kind of really small, many techniques and introduce that techniques to our code.
Okay, Professor.
Yeah.
Thank you.
Is that okay?
Yeah.
Thank you very much for your question.
Thank you very much for the questions. Okay, we have another question.
We could go for it.
So my question is related to the quantum. So you have said that we use the Hamiltonian matrices.
Yep.
So when we can compute these matrices, so you require some kind of quantum gates and
quantum what?
Quantum gates. When you can write a code, so you have to use the quantum gates to calculate these Hamiltonian matrices.
So quantum what? Sorry.
Quantum gates.
Gauge.
Gate.
A quantum gate.
Yeah.
No. This is again that's usual calculations, usual DFT calculation.
So that means.
So the calculation of the Hamiltonian matrix.
Yeah.
There are, to be honest, again there are many types of the terms.
Yeah.
But most of them are just usual, related to some summation, or sometimes we use the fast Fourier transformation.
Okay.
And there's some matrix multiplication. This kind of computations we are doing.
Okay, that means no quantum circuit design inside that one.
So at present, we have not used any quantum computation type calculations.
Okay.
It's different from the quantum chemistry calculation in this sense.
Okay. Thank you.
Yeah, but as far as I know that so far, any quantum chemistry calculations using the quantum computation is not real. Yeah.
Okay, thank you.
Okay, we have another question.
Thank you, Professor. We discussed yesterday, I asked you a question. I'm from NTUST. My first question would be about the diagonalization of the Hamilton. I was simply wondering at first if it was always diagonalizable or what approximation you would take for that.
For the diagonalization, sometimes we in many cases we use use dense matrix. But for the other method, sometimes we use the sparsity of the matrices. So, and we also use some technique called, I don't know whether it's known or not, but the Sakurai-Sugiura method. Yeah, and for this, we use the sparsity of the matrices.
Okay. Then, so your graphs, your figures showed that the diagonalization was the slowest computation part of the simulations, right?
Yes, with the first part, and for the large systems, the diagonalization part is the most expensive part, yes.
So I was wondering, since it's mainly matrix and tensor operations, I was wondering why.
Because of for the diagonalization, for the dense matrix, the computational cost is just proportional to the cube of the dimension of the matrix. It's simply because the computational cost, the computational amount, yes.
Why is CPU prioritized over GPU in your lab?
For the GPUs, sometimes, yes, for that, we now introducing only that part.
Okay.
But at present, we don't know much about that. I mean, we don't have the actual time. We are now checking that. Yeah.
Okay, thank you. And I had a last question, but that's more because I'm not very knowledgeable on quantum mechanics. I was wondering about the Hamilton energy decomposition, the Consham or Consham?
Yes, Consham equation. Consham equation comes from the DFT theory. And we have several terms coming from. So first, it's just for the one electron wave function. And it has the kinetic energy term and some electrostatic part, I mean, like a Coulomb potential between and coming from the charge density. And another thing is, which is specific to the DFT, and it's called exchange correlation functional. And for this, I mean, all this term is, I mean, we calculated in a different way. Sometimes in the real space, and sometimes in the reciprocal space, I mean, using the Fourier transformation. And sometimes just, yeah, so, sorry. But we have, I mean, this kind of techniques to do that.
Okay, so the decomposition is not an approximation, but a precise?
It's completely exact,
okay.
Yes.
Okay, thank you.
Yeah, thank you.
Thank you for the presentation. Yes, maybe the last questions.
Damara と申します。So my question is on the conclusion side, on the conclusion slides on your presentation.
Right.
I saw that the density matrix minimization has been done for 10,000 to 1,000,000 atoms, and I'm just curious why we stop at 1,000,000 atoms.
1 million.
Yeah. What happens if we go beyond that?
Yeah, we can do over, I mean, larger than that. But some political reason, we just thought that 1 million is enough at that time.
Oh, so just arbitrarily chosen as the...
At that time, this is already one of the biggest calculation in the world. And sometimes, I mean, just to get some useful information from the DFT calculation of such large systems, there are some just, it's not so clear. So sometimes the classical calculation may not be enough for this size, I mean this scale, length scale. Yeah.
But we can still expect the linear computation time for above 1,000,000 items.
Yeah.
Okay, thank you very much.
Thank you.
Okay, thank you for all the questions. We don't have any questions from the online participants. Thank you, Professor Miyazaki, for your presentations and for your answer and valuable insights. Please join me in giving a round of applause to Professor Miyazaki.
Thank you very much.
Thank you once again, Professor Miyazaki. We will now continue to our third keynote presentation. I would like to invite Associate Professor Nurwati to come up to the stage. So this is the CV from Associate Professor Nurwati. Associate Professor Nurwati is from the Department of Mathematics, Institute of Technology 10 November, Indonesia. And her main research focuses on graph theory. The title of her talk is Non-Local Adjacency Metric Dimension of Graphs. Associate Professor Nurwati, the stage is yours.
Yes. Thank you, Pak Sahab. Ladies and gentlemen, good morning. I'm Rinurwati. I speak English, but a little. So if there is any question, I will answer it in Bahasa Indonesia. I will sit. Yeah. Permisi.
Let's wait for a while for the slide.
Okay. In this presentation, I only write what is I have written in this my research PPT. Okay, I'm sorry for it. In ICoMPAC 2025, I will present my latest research in the field of graph theory, which is about metric dimension, title non-local adjacency metric dimension of graph. Next. This article I divided into 4 parts. That is introduction, preliminaries, main result, and conclusion. Next. The entire content of this article is summarized as in this abstract. Here, there are 6 things that I did in this research. That is, 1, I construct the non-local adjacency metric dimension of G, denoted by dim ANL G. 2, I introduce new graphs obtained from the degree corona product of two graphs. 3, determine and analyze the non-local adjacency metric dimension dim ANL of basic graph, center graph, and the degree corona product graphs. 4, provide upper bound. 5, characterization of dim ANL. And last, give an example of application of these concepts. Next. Metric dimension of graph developed by 2 ways, that is concept or its graph. The concept of metric dimension was first introduced by Harari and Milter to describe how vertices in a graph can be uniquely identified by their distance. 1 year later, Slater introduced metric dimension in terms of location numbers. Adjacency metric dimension introduced by Janisari and Omomi. Non-local metric dimension introduced by Klafsar, and non-local adjacency metric dimension of graph by me in this year. So the concept of metric dimension continued to be developed by researchers in this field by using different distance concept or by adding a condition or combining existing dimension concepts. Next. For developing graph here is about corona graph. Some variant corona graph have developed and those metric dimensions have resulted. Variant corona vertex introduced by Ruth and Harari and later extended by many research like Iswati about metric dimension of corona graph, Yero about recursive corona graph, Gopala Pillai about neighborhood corona, me about at corona, Nabila about bubble neighborhood corona, Valda leaf corona, and in this year I introduced the degree corona. Next. New variant followed, that is adjacent metric dimension, local metric dimension, local adjacency metric dimension, non-local metric dimension, non-local metric dimension, and now non-local adjacent metric dimension of graph by me. The study focused to the non-local adjacency metric dimension of basic graphs, center graphs, and enhancement of corona operation into the pre-corona graphs. Next. Here are the graphs that have been generated for their DIM A and L. The graph is basic graph and graph result from operating graph. Basic graph divided into two groups. First group is basic graph only, that is no vertex center. The example of paths and cycle. And second group of basic graph is graph with center. The example is strategic graph and complete graph. Next. Center graph is a graph that contains one or more center vertices, where a center vertex is a vertex adjacent to all other vertices in the graph. Figure 3 is an example of center graph, that is star graph. From figure 3, we can see that the only center vertex of graph Sn is vertex Vn. Next. The other group of graph is graph resulting from operation graph. That I discuss here is the corona graph and joint operation graph. Figure 5 is an example of corona graph, that is corona from Pn and K2. This graph is no center, but figure 6 is graph join from K1 and Pn, called as Van graph. This is a center graph with center vertex is V0. The next. Constructing the concept of non-local adjacency metric dimension, starting from what already exists, namely adjacency metric dimension. This concept using distant adjacency, dA, that is defined as dA VTI, is 0 for V is Ti, 1 for V is adjacent to Ti, and 2 for the other. So from here, the non-local adjacency metric dimension of graph C is defined by adding the non-local property as follows. Next. So a formal definition of non-local adjacency metric dimension for graph C is like this. The essence of dim ANLG is the minimum cardinality of the non-local adjacency basis of G. Next. So the calculation result dim ANL from G as mentioned can be obtained. This is dim ANL of basic graph Pn. Next. This is dim ANL of basic graph Cn. Next. This is dim ANL of center graph Kn 0. Dim ANL Sn is n minus 1 minus 2. Next, this is dim ANL center graph Fm, that is K1 plus Pn. This is a center graph. Next, this is dim ANL K1 plus Cn, that is graph wheel. Next, this is dim ANL of center graph Km plus Kn bar, that is n minus 1. The next. So now we come to the construction of the degree corona graph. The definition like this. And figure 9 is one of example of degree corona graph. That is the degree corona graph from Sn and Q1. This graph is with center, and this graph can be obtained by taking one Sn and as many sigma degree Vi of vertex Sn, and next connecting Vi of Sn with K1. So the result is like in the figure 9. The next. From this study, the properties related to the non-local adjacency resolving set of degree corona graph were obtained and are presented in lemma 3.9. From this lemma, is I use set for proof of the next graph. Next, this is dim NL of center graph GC and K1. The result is some degree Vi minus 1. Next, this is the fifth that I did in my research, that is provide a upper bound of dim ANLG. Based on the above research result, the upper bound of the non-local adjacency metric dimension is obtained as follows, that dim ANL of G is lower than n minus r. This dim ANL achieved by Sn. Next. This is the last that I did in my research. That is, give an example of application that is in a distribution network, but this is still in state of my thinking. Next. So from the discussion, it can be concluded that adding a vertex as a central vertex of a connected graph G one by one can increase the order of the graph, while the size of the non-local adjacency metric dimension of graphs obtained remain the same as the original graph. Thus, dim ENL K1 plus etc. plus G is the same as dim ENLG. So from here, the non-local adjacency metric dimension is an efficient network optimization. Next. Thank you.
Thank you very much, Associate Professor, for that presentations. We now have like more than 15 minutes for questions and discussions. Are there any questions or comments? Yes, please, Pradika.
All right, thank you very much, Pak Sab. So I actually want to ask about the maybe the improvement or maybe the development of the topic that you have mentioned before. So you mentioned about the non-local adjacency metric dimension, where one of the graph that you use in this topic is the basic graph. And as we know, when we're talking about a basic graph, we are not only talking about the undirected one. There's also a directed graph. So my first question is the same result that you mentioned on your research also holds for the directed graph? Okay, and what about the hypergraph? Or is there any certain conditions that need to be satisfied in order that the same result can hold true to the directed graph? So that's the first question. Thank you.
Okay, thank you, Pak Dika, for your question. Maybe I answer in bahasa Indonesia.
Yeah, sure.
Yeah. Basic graph, ya, about basic graph.
Iya, basic graph dan utamanya kan ketika kita bicara tentang basic graph itu kan gak hanya kita bicara soal graph tak berarah atau undirected graph, tapi juga ada directed graph. Nah, apakah hasil dari penelitian yang Ibu kerjakan ini berlaku juga untuk yang directed graph seperti itu?
Oke.
That's the translate.
Ketika orang graph itu bilang graph, artinya graph tidak berarah, gitu. Jadi dan graph itu bukan multigraph, jadi tidak ada sisi yang dihubungkan oleh lebih dari satu, dua titik yang dihubungkan oleh lebih dari satu, nggak ada apa namanya ini siklus ini yang dari satu titik bergerak ke satu titik.
The cycle.
Apa namanya? Ya, loop ya, tidak ada.
Loop.
Dan saya kira tidak berlaku untuk, atau mungkin berlaku tapi ya, mungkin juga tidak berlaku untuk yang graf berarah, begitu.
Yeah, I think it's an interesting comment because when you talk about adjacency matrix, it's a different characteristic when you talk about undirected graph and directed graph, right? So yeah, I think it's an interesting topic to be researched in the later development of your research. So yeah, thank you very much.
Oh, thank you, Pak Dika.
So just a short summary of the previous questions and answers. So Pak Dika is asking about what is the difference if we, instead of using undirected graph, and we want to change it into directed graph. So the main results that Professor Nurwati got in his research is for undirected graph. So the results will be, I don't know, maybe will be slightly different when we want to use it for directed graph or other types of graphs. Okay, do we have other questions from the on-site participants in the ballroom? Any other questions, please? Yes, yes, please.
Okay, good morning. Can Dr. Nurwati give us an example on the non-local adjacency graphs and what the purpose of searching the dimension is? And, saya bakal tanya di Indonesia juga. Ada contoh realnya nggak untuk non-local adjacency graph ini, dan sebenarnya tujuan nyari dimensinya khusus untuk graph ini itu apa? Gitu.
Contoh grafnya ya graf apa saja Pak Mas Jalu. Tapi untuk maksudnya untuk mencari non-local adjacency kan di graf itu di konsep metric dimension itu seperti saya jelaskan tadi bisa menggunakan definisi jarak yang berbeda, dan biasanya kan kita cuma menyebut dimensi metrik gitu aja. Berarti metriknya adalah jarak biasa, yaitu jarak antara dua titik. Dalam hal graf, maka jarak dua titik itu adalah banyaknya sisi dalam lintasan terpendek yang menghubungkan kedua titik itu. Tapi dalam ini saya mencari memperkenalkan konsep dimensi metrik dengan menggunakan jarak ketetanggaan. Sebenarnya sudah ada jarak ketetanggaan tersebut seperti yang saya sebutkan, dia 0 kalau dua titik itu berimpit, 1 jaraknya kalau dia bertetangga, dan yang lain hanya dikelompokkan menjadi 2 semuanya, apapun kondisinya. Nah, seperti itu. Jadi keinginan saya adalah bahwa kalau seperti itu untuk yang adjacent itu bisa untuk lokal, bisa non lokal. Non lokal itu untuk membedakan titik-titik yang tidak bertetangga untuk non lokal. Jadi kenapa saya cari yang non lokal? Saya bertujuan untuk mendapatkan dimensi yang lebih kecil. Jadi misalkan kalau saya punya suatu graf G, dimensinya itu 5, dan dimensi metrik maksudnya, dimensi metriknya 5, kemudian saya dengan memperkenalkan dimensi non-metrik tetanggaan non-lokal ini, ternyata dim G tadi, dim ANL-nya itu menjadi lebih kecil, misalkan 4 misalkan. Maka saya merasa itu, oh berarti berhasil ini ya saya. Karena tujuannya adalah metric dimension itu sebenarnya kan optimasi gitu, optimasi graf. Jadi kalau saya bisa menemukan dengan suatu konsep itu dimensinya dibandingkan dengan dimensi biasa itu ternyata dimnya lebih kecil, maka optimasi saya adalah efisien begitu. Begitu Mas Jalu.
Baik, terima kasih Bu. Thank you very much.
Okay, so it's quite hard to understand the question and the answer. So the one thing I understand is when usually other people use standard metric, but in this research, in Professor Nurwati research, he used adjacency matrix, and also it is using the local one. So do we have any other questions? Okay, maybe I have one question. So Professor Dunwati, you mentioned before so this topic is also related to optimization. So are there optimization methods that can be used to count the metric dimensions instead of maybe using the analytical approach? And what kind of optimization we can use? Yes, optimization methods, tool, or maybe how you can obtain the dimensions. Yeah.
Optimizing graph degree corona with non-local adjacency metric dimensions like this.
Yes, I mean how let's say, how do you get the number? How do you get the dimension?
How you get to number?
Yes.
Yeah, by the definition of this metric dimension.
So maybe if we have another types of graph, or maybe we have graph with higher dimension, how if we want to count the dimension, how should we do it?
Maybe by an algorithm, yeah. With my student S3 doctoral, dia menggunakan mencari dimensi metrik itu melalui jenis-jenis dari himpunan pembedanya. Nah, kardinalitas dari himpunan pembeda itu kan nanti menjadi dimensi metriknya. Nah, itu bisa dicari tidak manual. Selama ini kan saya manual gitu mencarinya. Ya, begitu saya dapatkan pola, maka saya buktikan, saya tunjukkan bahwa itu berlaku. Nah, si mahasiswa S3 saya ini mencoba menggunakan algoritma heuristik. Seperti itu. Banyak di situ algoritmanya, dan beliau bilang begini, ibu kalau ibu apa sih ini konsep yang ibu tawarkan, banyak itu saya lihat gitu. Jadi saya nanti tinggal membuat algoritmanya begitu. Jadi like this.
So summarizing, so what Professor Nuwati did in her research is usually let's say if she has a graph and then she tried to count, let's say the dimension manually, and then she tried to get the pattern, and then from that she continues to, let's say, to build the theorem, the lemma, and so on, and then she tried to prove it. And then she also has students, so she said that for computing the dimension, we also can use some heuristic algorithm. So I don't know how the detail of the heuristic, but let's say we can try to count the number of elements. Yeah, the dimension metric. Okay, do we have another questions or comments from the audience in the hall? So maybe we can, that's all for this third keynote speaker. Thank you, Associate Professor Renowati, for your presentation. Thank you once again. So we will now continue with our last keynote speaker. So the last presentation will be delivered by Professor Agus Hassan. He is joining us online through Zoom. I would like to invite Professor Agus Hassan to please turn on his camera and microphone. Professor Agus Hassan, can you hear us?
Yes, I can hear you. Can you hear me?
Can you make it louder?
Yes. Can you hear me?
Yes. Very clear. So it's my pleasure to introduce our final keynote speaker, Professor Agus Hassan from Norwegian University of Science and Technology, Norway. So this is his CV of Professor Agus Hassan. So Professor Agus Hassan is a researcher in cybernetics, robotics, digital twins, energy informations, and data-driven discovery. The title of his talk is The Role of Mathematics in Energy Transitions. Professor, the time is yours.
Maybe I'll share my screen with you. Can you see my screen?
Not yet.
Can you see my screen now?
Yeah, we can see it in the Zoom, but we are waiting for the connection in the ballroom.
Yes.
Okay, now we can see it.
First of all, thank you very much for the introduction. It is an honor to be here giving a talk at the International Conference on Mathematics, Pure, Applied, and Computation 2025. As we know that throughout history, mathematics has powered every great transformation, from navigation to communication, from medicine to finance. And today, we are confronted with the challenge of our time, and that is with regards to energy transition. Behind every wind farms layout or solar farms layout, also behind every battery optimization algorithms, every carbon market forecast, for example, lies a web of mathematical models that translate complexity into clarity. And if you look into the big picture, the energy transition is often portrayed as the story of engineer or policymaker, but actually there are many mathematicians who play equally roles on the story of energy transition. So today we are going to talk about the roles of mathematics in energy transition. This is the outline of my talk today. I will start with the introduction, and then we will discuss three areas where mathematics play a big roles. The first one is about wind farms development. The second one about energy storage, and the third one is about smart grid. And then I will finish this talk with some remarks. So what is energy transition? As we know that the energy transition is the global shifts from fossil fuel-based energy system, which is mainly based on coal, oil, and gas, toward clean, renewable, and sustainable energy resources. And then this is the key drivers for energy transition. The first one is there is a climate change happening now. There is a need to cut greenhouse gas emission. We can see that in many places around the globe, the temperature fluctuating quite extremely. And then we also have renewable energy booms due to the falling costs of solar and wind. And then there are also technology innovation such as electrification in the transport sector, either car electrification, for example, or maybe in maritime area. And then also there is a push from the government with policy and investment in order to achieve net zero target. So this drivers and definition is something that we knows what it is, but there are some challenges that maybe not many people realize For example, like the wind and solar are considered as variable renewable energy because it really depends on weather. So we can actually predict the weather for a certain period of time, but also the weather always changing. So in order to ensure that the grid is stable, the supply is stable from these resources, we need to have like energy storage. The problem is that the energy storage is really expensive up until now. So it is not a trivial things to change the or to transform from base load or fossil fuel based energy system into more clean energy. And then we also have a challenge with industry decarbonization. Most industry like steel or cement, it's really hard to be decarbonized because by the definition, they actually produce CO2, for example, or other greenhouse gas emission. Changing the renewable resources or to power this industry is not trivial either. And then also every country in this world were created not equal. So there are some countries who has abundance access to renewable energy, but there are also or many other countries that is not having that privilege. Also, when we're talking about transition, means that not only the technology but also the people need to be educated. So there is workforce reskilling and also transition support. Now let's see or discuss a little bit about the transition in Indonesia. So Indonesia is one of the few countries who always miss their energy transition. The current energy resources in Indonesia consist of coal, oil, and natural, which is basically fossil based. And then there are several other renewable, for example, like hydro, geothermal, solar, biomass, and wind. But if we look into the data, the proportion is not really favorable because you can see that the fossil fuel base consists of 85% of the energy generation, while the renewable energy is only 15, and this 15 coming only from hydro and geothermal, while solar, biomass, and wind, their contribution is below 1%. Okay. So there is a challenge also when we're talking about energy transition in Indonesia on how to boost the renewable energy, for example, not only relying on hydro, but also maybe we need to develop also solar and wind. And also, if you look into the news, there are also some initiative from the government that is to look into nuclear energy. But this is a bit controversial right now. But it could be a really good alternative in the future. Now, what I would like to talk about today, we will talk about wind because wind energy, it's clean, not only clean, but also we do have some potential in Indonesia. For example, in East Java, you are familiar with this map. So this is a map of East Java, and then the map here showing the average wind throughout the year. So for example, let's say that the government wants to develop wind farms to support the energy transition in East Java. And then normally if you want to build a wind farms, the mean average of this wind speed should be around 6 meters per second. If you look into the map, there are 3 possible sites around Ngasem, for example, around Probolinggo, and also in the around Banyuwangi, in the north part of Banyuwangi. Now, there are several questions about this site. For example, like what is the optimal location for establishing a wind turbine site? Because developing wind turbine is not cheap also. Like for example, for one turbine with the capacity of 1 megawatt, the cost could goes up to 1 to 2 million US dollar. So if we want to determine the optimal location, we need to do some simulation. So we need to be able to develop a high fidelity model of wind turbines and also wind farms. And then based on that model, we can do what if scenario. And this what if scenario can give us more informed decision when we want to decide the best or the optimal location of these wind turbines. There are also questions about the required numbers of wind turbines, for example. What is the procedure for operating the wind turbines? Are there any environmental or wildlife concerns? And also, what is the proximity to existing power grid infrastructure? For example, here, if you look into the only means of the wind speed, the best location could be around Banyuwangi, because the average speed is around 7 meter per second. So this is higher than the other two locations. But then the location is offshore. Now, if you go offshore, the things become more complicated. For example, like definitely it's more expensive, and also in order to do maintenance for offshore facility is not cheap either. So there is a trade-off between the amount of power that can be generated and also the costs associated with the maintenance and installation, like that. Okay. Now I would like to give you a short course about wind turbines. So this is a typical modern wind turbines. This diagram is called the nacelle. The wind turbines, the modern wind turbines, normally horizontally axis like this, and then it consists of 3 blades. The blades is connected with the pitch system that can regulate the pitch of the blades, and then once the blade is rotating, the energy will be translated from low speed rotation into high speed rotation using this gearbox. And once this high speed rotation rotate the generator, it will convert the mechanical rotation into electricity. Now the electricity will be connected into the grid afterwards. But before the grids, normally these wind turbines will be connected to the energy storage, because it will ensure the stability of the electricity that is produced from the grids, or from the wind turbines into the grids. There are also another components here, for example, the yaw control here in order to rotate the wind turbine, and that is to ensure that the wind turbines always face the direction of the wind. Okay. We also have some sensor here, for example, anemometer. The typical power that is being produced from a wind turbine looks like this. So there is a cut in speed that is where the wind farms, wind turbines will start to rotate. For example, like the typical cut in speed is around 4 meter per second. So if the speed's below that cut in speed, then the wind turbines will not rotate, but once it hits that limit, then it will start to rotate and start to produce the energy. And then you can see here there are 2 major trends. The first one is transient. This is region 2, and then region 3, that is where we have a plateau or stable supply. The most optimal one is actually the region 3, that is where we get a steady supply from the wind turbines to the grid. And then you might wonder how this become really flat. It's because in the turbine system, we have the controller to ensure that the energy will be stable. And that is due to the pitch system and also the yaw motor. So this pitch and yaw control, basically the main control of these wind turbines, will ensure that for every wind speed that is goes from rated velocity to cut off velocity, the supply will be stable. Okay. But then if we have, for example, storms where these blades will goes very fast, then we need to break the turbines such that it will not destroy the component. So you can see here that when the speed is above some limits, then we need to stop the wind turbine. Okay. But this is a bit typical power output that can you obtain from wind turbines. Now, the question is that in what way that mathematics can contribute to wind farm development. As I mentioned to you, the first one is about what if scenario, because wind turbines project is really expensive. So when we want to determine the best location, for example, then we need to have a model. You can see here that this is a project that was funded by Equinor. Equinor is some kind of like Pertamina in Indonesia. We do this project a few years ago, and the objective of this project is to determine what is the how many numbers of wind turbines that is needed in order to repower or power this oil and gas platforms in the North Sea. So our solution is that there are at least 11 wind turbines that need to be developed, and then the next question is, for example, in which location, because the location should be close enough to the platforms, but also has higher or the highest potential, which means that the means speed need to be above 7. So when we do this simulation, basically you can see here that we use mathematical model in order to model the winds, for example, to model the power for each of these turbines. So it looks like engineering works, but actually there are a lot of mathematical model that involves in this simulation. So this is one of the example where mathematics can play a role, and that is on how to develop a model accurately such that we can do what if scenario and minimize the cost, for example, and also optimize the operation. Another example of mathematics is when we want to design wind turbines blades. You can see here that when the blades start to rotate, there is a lot of turbulence happens, and then if we have better knowledge about the turbulence, then we can design the wind turbines in much optimal way. So then we go with the computational fluid dynamics. In computational fluid dynamics, when you want to model turbulence like this, there are several approaches. The first one is direct numerical simulation, and that is basically to solve Navier-Stokes equation numerically, and then you will get a very high resolution model. But then the problem is that it is really computationally expensive to solve Navier-Stokes equation. Another option is that goes with you introduce some assumption, and then you reduce the complexity of the equation, and then you end up with large eddy simulation. For example, you can see here that the large eddy simulation capture some aspect of Navier-Stokes, but then even though not really accurate, but large eddy simulation gives you really fast result. But even though it is fast, it's still not fast enough. And then you can go with introducing much more more assumption, and then you can end up with, for example, Reynolds average Navier-Stokes, which is much faster than large eddy or Navier-Stokes. But then you can see that the accuracy is not that good. But it might be that for design, even though Rand's model is not really accurate for design purpose, it might be that this is good enough. Now, why we also need to consider this type of turbulence? Because in wind farms, the wind turbines location actually affected the power output of other wind turbines. In this particular example, we see here that the turbulence causes this disruption of the second wind turbines, and then what happened is that the first wind turbines can give you a maximum power output, like 100%. It's of the rated capacity. But then the second wind turbines, due to this turbulence, will only have maybe like 70 to 80% of its rated capacity because of this turbulence. So if we able to understand this phenomena, then we can design a better blades such that the wind turbines, the second wind turbines, can still or yields a better power output. Okay. Another example is in layout and spacing. This project is funded by Horizon Europe, and then we do it actually now. So this figure, this is coming from one of the wind farms in Denmark, and then you can see here, this is the actual phenomena of the wake that I show you in the previous slide. So due to turbulence, the turbines that is located will be influenced by this turbulence and then will produce less energy than it expected. So one of the things that we can do is that to reposition these wind turbines. For example, here we have a baseline. This is a bit random actually. And then we can use, for example, like genetic algorithms in order to find much optimal location that produce the energy close to the rated capacity. Okay. So this is the baseline. For example, this is a random location. We run it, the algorithm using genetic algorithm, and then we find a much better location. We could also use another algorithm, for example, like PSO, and then you can see here that both the GA and PSO gives quite similar result. Okay, and then the result is definitely increase the total energy production from these wind farms. Another example of mathematics is in battery storage. As I mentioned to you that if we want to stabilize the grid, we need to ensure that the supply, the electricity supplies coming from wind turbines need to be constant. So before the electricity goes into the grids, normally we need to have like energy storage, battery energy storage, and the most common energy storage is to use lithium-ion battery. Now, if we think about this system, then one important thing is that we need to be able to estimate the state of charge, of the state of health of this battery. And then you can do this by looking into the mathematical model and then also implement, for example, like Kalman filter. So the mathematical models of lithium ion is nonlinear, and then the measurement equation also is nonlinear. So we can, for example, linearize the system and then use Kalman filter, calculate the gain such that we can be able to estimate the state equation or the state of health or state of charge of this particular battery system. This information is really crucial because we will know the exact amount of capacity that is within this battery. The last example that I would like to show you, this is about grid, smart grid, in particular regarding grid balancing system. So what is grid balancing? Grid balancing is activity in order to balance between supply and demand. So the problem is that why we need to have this balance it's because if the energy that is produced less than the demand, then we will have blackout. Okay, but vice versa, if the energy that is supplied much higher than demand, then basically the electricity price will fall down. So there is no value, or the value will be decreased. Now the problem here is that if we have, for example, a set of different energy resources, here we have wind farms, solar farms that is connected to the battery system. We also have conventional sources like maybe from hydropower, maybe nuclear, maybe coal, and then the question in here is that how to ensure that the supply will equal with the demand. So the demands, for example, can come from household, from office. We have like electricity charging. We have also factory and etc. Now, how to solve this? First, we can make a short diagram like this, simple diagram like this. In order to simplify the problem, let's say that we have 4 types of generator. Generator 1, that is hydroelectric. Generator 2, we have geothermal. Generator 3 and 4, we have wind and solar, which is considered as variable renewable energy. And the challenge with variable renewable energy is that this is not unpredictable, but it's changing over time. Okay, so first of all, we need to be able to predict the output from this renewable energy, and then use this information in order to calculate later the demand, also the supply. So let's say that we have 4 generator, and then we also have 4 customer, and then one generator can serve maybe 1, maybe 2, maybe 3 of this customer, and then you can see here that the line that goes from each generator shows how this generator supply the customer. So first of all, we need to be able to estimate or predict the demand of this electricity within maybe 24 hours ahead, and then use this information in order to solve some optimization problem. And in this optimization problem, basically the idea is that in order to how much electricity that is needed or generated such that the supply will be matched with the demand. Now I will show you an example of this optimization problem. It looks like this. So the idea here is that we want to minimize the cost associated with the power generation. So here, see, that is the cost of electricity for generator I times the power that is that can be generated from the generator I. And there is some slack variable in order to answer the positivity. And then here, for example, we have some constraint. The first constraint is to ensure that the supply and the demand it will be balanced. We also need to ensure that the solution, that is the electricity generated from the wind turbines, should be positive. And also we have also constraint in the transmission line, because some transmission line definitely has a limit. For example, it shouldn't be larger than 10 megawatts, for example, or 10,000 megawatts, etc. So if we solve this optimization problem, then the solution could be the amount of power that can be generated from each of this generator. And then this is an example of, we actually solve this in Python. And then we use some machine learning algorithms and also linear programming. And then this one is one of the input that we had. So this is demands, the predicted demands of the electricity from different customer. So for example, here the blue one that is from household, and then the red one that is from public facility, and etc. And then we use this information in an optimization algorithm, and then this is the solution that we get. So the first figure here, that is a figure of demand from each of the demands from each of the customer. And then the second figure here, this is the power flow from the generator to the customer. And then we also have the solution of the amount of power that needs to be generated from each of this generator. And then this one is the total generation cost over time. Okay. So all of these are some example of how we applied mathematics in real world problem, in particular with respect to the energy transition. So there is some remarks from my side. So the first one is that mathematics is the invisible engine driving the energy transition. In particular, it's transformed physical phenomena into models, prediction, and decision. The second one is that modeling helps us understand complex systems, for example, like wind variability, storage dynamics, and grid behavior. We also working with optimization that enable us to design and operate energy systems that are efficient, reliable, and cost-effective. Integrating demands mathematical coordination from forecasting and scheduling to real-time grid balancing. And we also working with advance in algorithms, data science, and computing, and accelerating innovation in clean energy technologies. And the last one is that mathematics provide the frameworks for turning sustainability goals into actionable strategies. So I think that's all from my side. It has been around 30 minutes. So maybe we can go with the question and answer. Thank you very much.
Thank you very much, Professor Agus Hasan, for the presentations. So we now have about 15 minutes for questions and discussions. Any comments or questions? Yes, please, Pak Dika.
Okay, thank you very much, Professor Agus Hasan. So my question is, I'm really interested on one of your slides that discussing about the optimization of the electricity produced by the wind turbine power plants. So what did you shown to us recently is a single constant optimization problem. And so my question is, have you tried to consider the optimization problem that you're working on this particular problem by using the multi-objective optimization? So for example, when we're talking about a power supply, we have in this case we're talking about wind turbine. We have to consider not only in what places where the wind current are the most powerful, but we have to also consider the threat of the natural disaster. For example, like we're talking about, is there any threat of flood or maybe earthquake and etc. So that's my question. Thank you.
Yes, thank you very much. That is a very good question. Of course, that when we look into the big picture, a complex project like this need to have like multi-objective. There should be like multi-objective optimization, not only minimizing the cost, for example, but also we need to consider the location with respect to the grids, for example. That is another constraint, and then also considering the regulation and etc. So up until right now, we only consider a discrete case, and that is basically looking into problem like this, not making it much more complex. But of course, that is possible to add or to formulate this problem as multi-objective optimization problem, and then you will end up, for example, with the solution in Pareto space. You have the different solution, and then the solution shows trade-off between one constraint to another. But that is, of course, possible to do it. But up until now, I haven't worked on that direction.
Yeah, I think it's an interesting topic to explore later on. So yeah, thank you very much, sir.
Yes, exactly. This is really interesting topics, especially if you consider much complex system. And also not only wind turbines, but because also when the wind turbine is connected to the grids, then we also need to consider, for example, like the interaction between one turbines and the other power resources. Yes.
Okay, a very nice question from Pak Dika. Do we have another questions from? Yes, please. Yeah. Yes, could you please come closer to the camera?
Okay, thank you very much for the question time. And I want to ask you about what factor affecting the base location of wind turbine beside the wind speed in the location? What factor affecting the base location of wind turbine beside the wind speed in the location?
Yes.
Because you have made the simulation in GA or PSO, so that there are other parameters affecting it.
Yes, exactly. There are a lot of parameters. First of all, of course, that the wind speed, the average wind speed throughout the year, but also not only the means, but also the variance of the wind speed. So if we look into the science of wind energy, the distribution is normally available. So we need to look into not only the means, but also the variance throughout the year. And also the diversity or biodiversity of the region. So for example, even though has here, there might be biodiversity like marine mammal, for example, that need to be considered. There are also people who lives as a fisherman. So those socio-economic aspect need to be also reconsidered. It might be also that if the wind farms is on land, the area is close to where the national forest, for example, located. So we need to avoid that. So not only technically, like wind speed, but also socioeconomics. Another things that we need to consider is that the proximity of the grid location to the grids, because for example here, if the location is quite remote, far away from the grids, then the cost of the development could be very expensive also. So there are a lot of factors that need to be considered when we want to decide the wind farms location. Yes. I hope it's answer.
Okay, thank you. And I want to ask again, when the wind turbine attached to the grid, there is a line resistance. Line resistance, is it affect the base location of wind turbine when wind turbine attached to the grid?
The problem is that when, for example, like if the wind turbines location is far from the grids, then we need to build an infrastructure, additional infrastructure. But then let's say that if we the electricity from the wind turbines cannot be connected directly with the grids, because the electricity from wind turbines is really fluctuated. If, for example, the fluctuation is higher, then it will affect the stability. For example, in Indonesia, I think the grid frequency is around, I'm not sure, it's maybe between 50 to 60 hertz. So if, for example, the electricity coming from wind directly injected into this grid, it will affect the stability of the grids. The frequency might drop, and even like drops in 1 hertz of the frequency will basically result in blackout. This is what happens in Spain and also Portugal earlier this year. So with respect to your question, I think the challenge here is that before the grids is the wind turbines or wind farms connecting into the grids, then we need to have like additional infrastructure like energy storage, such that the wind turbines can be connected into the grids in safely manner. Okay.
Oh, okay. Thank you.
Yes.
Thank you.
So that is the main challenge
Okay,
actually right now
okay.
to integrate
Oh,
the
okay.
wind turbines into the grid.
Okay, thank you for the answer.
Yes.
Okay. Do we have another questions? Yes.
Oke, terima kasih. Thank you for the chance. My name is Wery from Institut Teknologi Sumatera Lampung. My question is, I'm interested about the tools optimization that Professor Agus used in this in research. Why do you choose genetic algorithm and particle swarm optimizations? And what is stopping criteria do you use in this research? And how do you choose the tuning parameter in GA and PSO? Thank you.
Yes, thank you very much. So basically, why we solve this problem for a layout, for example, using genetic algorithm and PSO. So the answer is because if, for example, we have a high fidelity model of wind farms interaction, wind turbine interaction within wind farms, then the best way is that to calculate the gradient and then to solve optimization using that gradient. But the problem with that is that the wind farm system is too complex such that to obtain the gradients that can be used for optimization is not possible. So not only not possible, maybe it will take times also. So going with GA and PSO is the best we can do right now because it's simple, for example, and we can solve it in a faster way. So that is the reason. And then how to tune the parameters is basically we use a heuristic approach in order to find this parameters. We can do also like Monte Carlo simulation in order to find or to optimize these parameters. I hope it's answer the question.
Okay, thank you for the answer, Mr. Then, what is the stopping criteria do you use in this research for genetic algorithm and PSO?
Yes. So the criteria is that the power that is generated from the resulting layout should be maximum. So that is the optimization objective. Yes.
Okay, thank you. Is there any other questions? Yes, please.
Okay, thank you. My name is Vandra from ITS, and I have a question about the optimal location that you mentioned that first turbine mass efficiency is 100 and the second 80%. Then what's the optimal location? It should be the efficient optimal from the location.
Yes.
It's the minimum or maximum 50% or anything else. Okay, that's it. Thank you.
Yeah. So if we look into the rule of thumbs for utility scale wind turbines like this, the distance between one wind turbines and the other is supposed to be like 3 times of the diameters. Like for example, the biggest wind turbines in the world that is produced by a Chinese company, Dongfang, it has a rotor length around 150 meters. So the diameter could be like 300 meters. So for that particular wind turbines, the distance between one wind turbines and the other is around 1 kilometers. Okay. Now, even with such the distance, the wax effect or turbulence effect like this will still exist. So one way to solve this is that first of all, of course, that we have this distance like one kilometers, but also we can play with the pitch, and that is using pitch control in order to minimize the effect of turbulence. So instead of having like this, for example, like the first wind turbine have let's say 100% of the rated capacity, while the second one is 70%. So instead of having that composition, maybe it's better to reduce the output from the first wind turbine by changing the the pitch. So instead of 100, the first wind turbines could produce like 95%, but then the second wind turbines, because of the turbulence is reduced, then it will result in 80%. So there is a trade-off also. So first about and the second one is about how to control each of its individual blades such that the turbulence is not or can be minimized. Okay. So that is the answer.
Okay, thank you, Prof. Agus. That's it.
Thank you.
Thank you. So do we have another question? Okay, so I think that's all for the today keynote presentation. Thank you, Professor Agus Hassan, for the presentation and your answer. Please give a round of applause to Professor Agus Hassan.
Thank you very much for having me.
So that concludes all for keynote presentations for this session. We have had the privilege of hearing from outstanding researchers who shared valuable insights in this international conference. On behalf of the organizing committee, I would like to thank all our keynote speakers for their excellent contributions. I'd also like to thank all our participants, both on site and online, for your active engagement and thoughtful questions. Let's give one final round of applause to all our keynote speakers. This brings our keynote session to a close. The next section will begin at 1 p.m. as indicated in the conference program. Thank you everyone for your participation, and we hope you enjoyed the rest of the conference. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you to all keynote speakers for sharing such valuable insights. Your expertise reminds us how mathematics and computation continue to push innovation and understandings in diverse fields.
Before we move on, we would like to invite our keynote speakers to please come up on stage to receive a token of appreciation from ICoMPAC. To Professor Zhongshu Liu, Professor Tsuyoshi Miyazaki, and Professor Rinulwati, please join us on stage. We would also like to invite Professor Didi and Dr. Muhammad Iqbal to give the appreciation. Ladies and gentlemen, what an inspiring morning it has been. We have learned so much from our keynote speakers and we all deserve a little break. We will now take a lunch break for about an hour to relax and recharge. Lunch will be served outside the ballroom.
For our participants who are joining us online, please take this time to refresh and be ready for the next agenda.
Before we move on, we would like to announce that for the next agenda, participants will be divided into groups for the parallel session. Please listen carefully as we announce the room assignments for each group. For Group A, the parallel session will be in room Sriwijaya 1. Group B will be in this ballroom. Group C will be in room Sriwijaya 2. Group D will be in room Jenggala. Enjoy your lunch, have fun at the photo booth, and see you back soon. Enjoy your lunch, have fun at the photo booth, and see you back soon.
sebelah sana.
Oh,
Saya coba
iya.
masuk ya.
Di kameranya.
Ya, saya coba masuk, nanti suaranya pelan dengar. Ya.
Ini sama background masih on.
Oh.
Iya ini.
Iya. Kurang ke atas.
Iya.
Ini loh. Nah. Oh, gitu.
Tes 1. Tes 1 2. Tes 1 2.
everyone, and welcome to the parallel session. My name is Raihan Habibatiar, you can call me Raihan, and I'll be your master of ceremony for this highly anticipated discussion. But first of all, I want to ask some question. How is everyone doing? Is it good? Okay, I hope everyone is doing good, and I hope you're still feeling energized after the previous session. And in the next hours, we will be exploring several areas related to mathematics. This is a critical conversation for anyone in this field. And leading our discussion today is a recognized leader in this space with extensive experience in machine learning and big data field. And please join me in giving a warm welcome to our moderator, Mrs. Alvida Mustika Rukmi from Department of Mathematics, Institut Teknologi 10 November.
Dinita, Mbak Dinita. Saya diganti. Iya, iya Mbak Dinita.
Okay, there is a change. Moderator is Miss Dinita. Okay, for Miss Dinita, the stage is yours.
Ngomong apa ntar aku? Ngomong apa?
Jadi nanti ibunya mau memimpin moderator sama yang ini presentasi nanti.
Oh, presentasi untuk yang diajar kan?
Iya. Oh, ini saya, Bu.
Oh ya, berarti nanti aku cuma author ini, paper ini, waktunya segini gitu ngomongnya.
Iya, tapi ini yang pertama Pak ini, Bu. Pak Yusuf, Bu.
Oh ya Pak Yusuf, Pak Yusuf.
Tapi Ibu sambil mendampingi gitu, Bu, moderator.
Oh mendampingi moderator.
Mendampingi presentatornya.
Terus aku nih ngomong apa? Aku juga bingung. Ngomong gimana?
Saya juga kurang tahu, soalnya tadi saya di briefingnya Bu Aki ya.
Aku ngomong apa? Ngomong apa? Nih moderator aja. Iya, terus aku ngomong apa? Okay, thank you everyone for your attending. This time is time for the invite speaker. We present with the name of Muhammad Lutfi Shahab with the title is Shallow Physics Inform Neural Networks. Okay, yes, the time is yours.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. My name is Muhammad Lutfi Shahab, and I will present my small research I did during my PhD titled Shallow Physics Informed Neural Networks, or PINS. In recent years, many deep learning-based approaches have been developed to solve problems involving PDEs, and one of the most popular is physics-informed neural networks, or we usually call it as PINS. Many research typically use deep neural networks for PINs. However, deep networks usually need high computational costs. In this research, we are interested in employing shallow physics-informed neural networks, and we want to optimize the network with the Levenberg-Marquardt algorithm, or LM. We choose LM because it usually performs better if we have small problems or small neural networks. The objective of this research is to show that shallow pins optimized with the Leffenberg-Marquardt algorithm can produce accurate solutions, and shallow pins can outperform or has similar performance to deeper pins. Throughout this research, we will use a shallow feed-forward neural network with only 2 hidden layers. We will use the following notation, N to M1, M2, 1, to represent a neural network with 2 inputs, M1 neurons in the first hidden layer, and then M2 neurons in the second hidden layer, and 1 output. If we have the following weights and biases of the network, then the neural network function can be expressed as follows. Furthermore, if we want to enforce the initial and boundary conditions directly into the network structure, because in this case we will use neural network to PDEs, then we can use the following functions, where P and Q in this case are chosen such that U satisfies the initial and boundary conditions of the PDE. First, we want to discuss the use of pins for forward problems. In this case, we consider the following general PDE of the following form with certain initial and boundary conditions. And in forward problem, the objective is to approximate the solution UXT across the domain. And in this case, we want to approximate the solution using neural network functions. To do that, first, we need to choose some collocations from the domain. And in general case of pins or neural networks, so the weight can be learned by minimizing the following loss functions in equation 4. Usually, pins are optimized with the LBFGS or BFGS algorithms, and the required derivatives are computed using automatic differentiation. In this research, we propose to treat the problems as solving the following non-linear system. So instead of using the loss functions, in this case, we will try to solve the non-linear system, which then the non-linear system can be solved using the Leffenberg-Marquardt algorithm. However, the problem is when we use LM, usually LM is not available in many modern libraries. So in this case, we cannot use automatic differentiation to get the derivative. Later, for the numerical experiment, we will compare the use of LM and BFGS. And since we cannot use automatic differentiation for LM, then we need to build everything from scratch for the implementation. So in this page, we show how to compute the derivatives of a neural network with respect to the input variables. So we have 2 input variables in this case, so X and T. And assuming this is the output of the neural network, and to make it easier, we can rewrite the network operations as follows. So we write it in several steps. And then from this, we can try to get the formula for computing UX, UXX, and UT. Because in this case, we discussed the use of neural networks for solving PDEs. And in PDEs, usually we will need the derivative of U. So we need the formula to compute UX, UXX, and so on. And then the tilde here represents the function before enforcing the initial and boundary conditions. So when we enforce the initial and boundary conditions, then the final approximations of U and its derivative are given by the following formulas. And once we compute U, UT, UX, and UXX, we can plug this into the nonlinear system. And we can proceed for the training process. So in this page, we show an accurate architecture of pins. So where the yellow block here represents a standard feed-forward neural network that can be used, for example, if we have regression or classification problems. In this case, I only draw one neurons in the hidden layer, but actually in the implementation, we can use multiple number of neurons. So I just want, I draw only one node in this case. And then in pins, since we need to compute the derivative of U, so we should add an additional networks. So we add an additional networks here to compute. Let's say here we need to compute UT, and then we need additional networks to compute UX, and so on. And then we need to combine all these networks into a single complete network to build the architecture of pins, which then these all the terms, we can use it to compute the loss function or the nonlinear system of the problem we need to solve. Remember that we will use the 11-bit algorithm to solve the nonlinear system, and LM needs Jacobian to do the update step. So to compute the Jacobian, first we need to reorder all the weights of the networks into a single column vector, like this one. And since we have chosen some collocation points, so in the beginning, then we can build the Jacobian matrix from the system. And then to compute the element of the Jacobian matrix, first we need to obtain the formulas for the derivative of u, ux, uxx, and ut with respect to the weight of the network. Because the one who we need to update in this case is the weight of the network. These are some formulas to compute the derivative of u tilde t, and so on with respect to the weights in capital W2 here. So this capital W2 is the weight between the first hidden layer and the second hidden layer. And note that we need different formulas for computing derivatives in different positions of the weights in the network. So if the weight is further from the output, then the formulas become more complex. From the previous formula, and since we enforce the initial and boundary conditions, so we can proceed to compute the final expression for the derivatives with respect to the weights as follows. And then with these formulas, we can compute the Jacobian, and then we can use the following update step for the 11-bit algorithm. Then when we try to compare the 11-bit algorithm and BFGS, we notice that the Jacobian for LM and the gradient for BFGS are connected with the following formula, or in the matrix notation, it is given as follows. Actually, this is very interesting because for for LM, we want to solve a nonlinear system, and for BFGS, we minimize a loss function. So it's two different problems, but there is a connection between the Jacobian and the gradient of the problem. So it is connected with the following equation, equation 12. So if we assume that the time for computing the Jacobian and the gradient are similar, then the primary difference in computational cost between LM and BFGS lies only in the update step. Next, we see the formulation of pins for inverse problems. We consider the following general PDE of the following form, where lambda here is the set of unknown parameters to be identified together with the weight of the network. And to do that, first we need to choose some collocation points and the corresponding solution at these points. And in general case of pins, the weights of the network can be learned by minimizing the following loss function. As in the forward problem, we treat this case as solving the following nonlinear system, which then the nonlinear system can be solved using the 11-bit algorithm. And the derivative of the neural network function with respect to the input variable can be computed as in the forward problem. We also follow similar procedure to compute the Jacobian. However, in this case, we also have lambda as an additional trainable parameter to be optimized together with the network weights. Then the Jacobian is given as follows, and the derivative of u, ut, u, and so on with respect to the weights also can be computed as in the forward problem. Again, as in the forward problem, the Jacobian for LM and the gradient for BFGS in an inverse problem are connected with the following formula. For numerical example, for forward problem, we consider the following Burger's equations. So we choose the following function. We choose the following function to enforce the initial and boundary conditions. Then for training, we choose 10,000 collocation points, and we use a network with 2 hidden layers with 25 neurons in each layer. And since the computational cost for the update step of the 11-bit algorithm is typically longer than BFGS, then we train the network with LM with only 4,000 iterations, and while for BFGS we use 20,000 iterations. So this is the neural network solution obtained by the Leffenberg-Marquardt algorithm, and these are the solutions at 3 time slices from LM and BFGS compared to the true solutions. The solutions appear similar, except if we zoom at a certain position, we will see that LM is more accurate than BFGS. And then in this graph, we show the training loss from LM and BFGS, and we observe that LM is around 5 orders of magnitude better than BFGS. And note that this is obtained by LM with only 4,000 iterations, while BFGS in this case use 20,000 iterations. And then when we compare the error relative to the true solution, so for this equation, for the Burgers equation, we have the true solutions. And when we compare the relative error to the true solutions, LM far outperforms BFGS while requiring significantly less computational time. Note that the original paper of Pins also discussed the same equations, and we see that our result with only 2 hidden layers also slightly outperforms the results obtained in the original paper of Pins, which use 9 hidden layers. And then in this table, we compare the network with different number of neurons in each hidden layer from 5, 10, 15, and so on. And we see that increasing the number of neurons results in lower loss or error values. From our perspective, the network with 15 neurons already produces good results with reasonable computational time. For the inverse problem, we consider the same Burgers equation as in the forward problem. However, in this case, we need to treat lambda 1 and lambda 2 as unknown parameters to be identified together with the weight of the network. And these are the settings we use for the experiment. First, we show the training loss from LM and BFGS, and we observe that LM is around 3 orders of magnitude better than BFGS. And in this graph, we show the evolution of the estimated parameters for lambda 1 and lambda 2. And we see that LM converge faster to the true solutions, to the true parameters than BFGS. Then this table shows the obtained parameters from LM, BFGS, and the original paper of Pins. And in this table, we show the APE, or absolute percentage error, which shows that LM outperforms BFGS. We also see that LM with only 2 hidden layers is comparable with the results in the original paper of Pins with 9 hidden layers. And then in this table, we compare the network with different numbers of neurons in each hidden layer, and we see that, again, in this case, the network with 15 neurons has good results with absolute percentage errors below 1% for lambda 1 and lambda 2. We also have another example with the Allen-Chan equation for both forward and inverse problem. However, we do not show time. So from this research, we can give a small suggestion that if we have easier problem or PDE, then we can use smaller network. And if we have harder problem to solve, then we need deeper or wider network. Okay, that's all from me, and thank you. And I will be happy if you have any questions or comments.
One has a question for him. The time for Q&A is 5 minutes.
There is one question.
Okay.
So in your research, you are using CNN?
No, just like a standard feed-forward neural network.
Yeah, yeah. So the point is that you are talking about the layers, 1 layer, 2 layers in feed-forward networks, yes?
Yeah, I use 2 hidden layers.
Yeah, hidden layers. So how we can decide how many hidden layers are required for our model? Because some people are using 4, 5, 6, 7. Some people are using 2, 3. So how we can decide the optimum numbers of layer in that LSTM, any kind of neural networks? It is general terms I'm asking.
So yeah, that's a nice question. So in this research, we show that So how much number of hidden layers we need to use in each problem? Like if we change the problem, usually we need to adjust the number of hidden layers.
Yes.
And in case of solving PDE, so because in this research I talk the use of neural network to solve PDEs. So let's this person, this is the original research. I can say this is the main research that use neural networks to solve PDEs. And in some of their examples, they use a neural network with 9 hidden layers.
Okay.
And then for the optimization, they used BFGS or LBFGS. So it can depend on the problem you want to solve, and then let's say you can see how is, if you have any experience about maybe the solution will be like this, so you will gain an understanding that maybe I should try 2 hidden layers, maybe I should try 4 hidden layers, and then if you try to solve it and then you will get some errors, you can check whether, okay, this error is still big, so I need maybe to add more hidden layers. But in this research, I show so this is the original paper with 9 hidden layers. So in this research, I use only hidden layers.
Okay.
But I propose to change the problem. So usually when we deal with machine learning, deep learning, neural network, we need to minimize loss function.
Yes.
So in this research, I changed the function into solving nonlinear system. And then I solve the nonlinear system instead of minimizing the loss function. So with that method, use smaller networks with smaller hidden layers, and then I can also solve it faster.
Okay, that means numbers of networks increases, so possibility of layer is also increasing. Yes or not?
Can you repeat the question?
Suppose the network size is large, so the possibility of layer is also high if size of network is large. Because you told that you are using the less number of network size. Suppose if you increase the size of your network, so it is possible to increase the layer of hidden layer?
So I don't understand. What do you mean with the size of the network? Is it the size of the, like how many weights we have in the network? Yeah. Usually if we use more hidden layers, then we will more weights to optimize.
Okay. Thank you.
That's it. Any other question?
Okay, one more question. Okay, we will continue to the first presenter.
Thank you very much.
Okay. Thank you. Thank you for your presentation, Mr. Muhammad Lutfi Sahab. And we will continue to the first. Okay. Okay, we will continue to the next presentation for the general presenter with codes B68 with the name Mr. Bandung Ari Sanjoyo, Mr. Mahmud Yunus, and Mr. Nurul Hidayat with the title is A New Initial Approximation Bound in the Duran Kernel Algorithm for Finding Polynomial Layers. The time is yours.
Okay, thank you. Bismillah. Now I will present my little research. This research comes from my lecture about matrix computation, with the title is New Initial Approximation Bound in the Duran-Kender Algorithm for Finding Polynomial Zeros. This problem is very basic problem in computation. This problem is inspired from roots function from MATLAB. That if we use roots function MATLAB with polynomial degree 25, so there are so many error atau significant error of the root. Tidak bisa. Next aja. Okay. Next. Okay. The polynomial zeros can be expressed like equation number 1, that's px equal to 0, and I take a monic polynomial, so the coefficient of x power n is 1. And the equation number 1 can be expressed as equation number 2, x e, the root of e, the root e root, equal with x minus px divided by x minus xj, where e is not equal to j. So this is very simple equation to find the root of polynomial, and from this equation we can find the xe from 1 to n, parallelize. Okay, so if we base on the equation 2, we can express the input like that one. We have array with n plus 1 elements. That's express the coefficient of px, and the output is array x or vector x, where the xe is the root of px equal to 0. So from the equation 2, we will express in the algorithm in 3 steps. And this algorithm is called the Duran-Kender algorithm or Weierstrass algorithm. The step number 1 is setting the initial value xe power 0. Like other method for root finding like Newton-Raphson or bisection or other one, the problem is one of the problem to find the root is setting the initial value. So in this research, I try to make a new bond to setting the initial value. And case of step number 2 and 3 is not changed. Next. And the most setting the initial value come from Cauchy bonds with the Cauchy using formula number 3. The bond of the root is R equal to 1 plus maximum of the coefficient of the polynomial. So from equation number 3 can be expressed as algorithm like that. And this algorithm is extra space constant. That means that memory atau extra memory is not depend on the input. So we call it the constant extra space. And the number of complexity of the algorithm is On. So the Cauchy bond is very simple. The next one is number 2. About Lagrange bond. The Lagrange bond also require constant extra space and has a computational cost On square. So this is more computation cost than Cauchy bond. The next one is number 2, 3. Next, about Albert bond. Albert, they change the polynomial polynomial transform, and get bond of the root radius of the root complex is R equal to A2 divided by N plus R0, where R0 is root of equation 6. Next. Also, this algorithm, Albert Bond, they have computational cost of ON square. And also the Albert Bond is constant extra space, so the memory is not depend on the input. Come from this three bond about setting initial value in the polynomial. That is, each of this bond has own computational characteristic and accuracy. However, they may not always provide the tightest possible radius, especially for polynomial with specific coefficient structure. So come from this, I motivated to develop the new bond, such as those proposed in this paper. I propose two new bonds. The number one is, next. The proposed bond number one is come from theorem 1 and theorem 2, and from the two theorem I derive the new bond from equation 10, and I get the next one. Next. I get equation 12 and equation 13. So from equation 12, the right hand side is still variable r. So we cannot set the bond, and I make a new function from equation 12. I call the GRA function, and I remove the 1 divided by r power k min 2. So I get the 13th equation. Next. From this equation, I compare using graphic of the two functions, graphic of f and graphic of g. So from this graphical, I take the graphic that is tightly to the root. So the tightly graphic is R equals sigma. That I call this new bond number 1. Next. And I also find the other bond because the root of the polynomial must
almost over.
Almost over. Okay.
Accelerate the
Okay.
presentation.
The result aja graphic of the terus next. And then this is the good bond is lambda maximal bond. This is my bond number 2. And the next, that's the conclusion. Habis. Yes. From the experiment, I conclude that the choice of initial approximation selection significantly influenced the convergence of behavior. The choice of initial radius directly affect the speed of convergence of the Duran-Kender method. Newborn 1, while ensuring convergence, tend to produce excessively large radius. This can lead to the inefficient in computation error iteration. But the lambda bond derived from the dominant eigenvalue of the companion metric consistently guaranteeing that all roots lie within the complex circle and support fast stable convergence. I think that's all.
Thank you, Mr. Bandung Ari Sanjaya. This is a presentation for the general presenter, and the time for Q&A is 5 minutes. And for the anyone has a question for the presentation? Okay.
Okay, thank you, Pak Bandung. So I have a question. Did you compare, let's say, the one you proposed in this research? So if, let's say, if we use the Duran-Kernel method with your approximation, how is the result compared to maybe if we use, you mentioned before about Cauchy's bound and Abbert's bound? Yeah. Thank you.
From my experiment, there are so many graphics. That's I compare with standard Duran-Kernel that using initial value Cauchy, Albert, and Lagrange, 3 types of initial approximation. I compare with my proposed, the newborn one and the lambda max, but the better in case of number computation, in case of iteration, also in case of accuracy, the maximal bound is the best. I have some experiment from the graphics. So I propose to bond, new bond and lambda maximal bond, but the lambda maximal bond is the best. Also better than if we compare with roots function from MATLAB, built-in function MATLAB roots. But the polynomial, the degree of polynomial until 25. Greater than that,
okay.
I don't try.
Okay, thank you.
More question? Oh. I think is enough. This is time for giving certificate. Okay, we will continue to the next presenter, the second general presenter with B71 with the name Mr. Nurul Hidayat, Mr. Nuansa Cahya Muhammad, Mr. Muhammad Isa Iriawan, Mr. Muhammad Lutfi Shahab, and Mrs. Diah Utami Kesuma Dewi with the title is Cryptocurrency Price Prediction Using Informal Model. The time is yours.
Ini yang show. Ini. Ini.
Saya upload, nah harusnya bisa.
Oh, diklik lagi.
Sebentar ya, Mbak. Saya.
Don. Wait.
Good afternoon, everyone. My name is Dia Hutami Kusumadewi, and today I will present a research entitled Cryptocurrency Price Prediction Using Informer Model. This study was conducted with my authors from the Department of Mathematics at 10 November Institute of Technology, Indonesia. We wrote this paper based on our original research, and I'll explain it step by step in this presentation. To begin, let me give you a brief overview. Cryptocurrency has become a very popular digital asset, but is still known for its high volatility, which makes prediction challenging for investors. To handle this, we need forecasting models that can capture long-term dependencies in price movements. In this study, we use the Informer model, a deep learning model that improves efficiency compared to the standard transformer architecture. We use historical price data from February 2015 to February 2025 and test several prediction horizons 1, 7, 30, and 90 days with two window size 120 and 180. Our results showed that Informer consistently outperformed Transformer in both accuracy and computational efficiency, especially with longer data windows. In summary, Informer provides more accurate and faster cryptocurrency price forecasting. Let's move on the background. Investment is an activity of allocating capital with the expectation of gaining profit. In recent years, cryptocurrency has become a major investment choice worldwide. As of January 2025, the global cryptocurrency market capitalization reached around 3.69 trillion US dollars, which is an increase of more than 113% compared to the previous year. In Indonesia, the adoption of crypto assets has also grown rapidly. The number of crypto users reached 21.3 million as of September 2024, and the national transaction volume reached around 33.7 trillion rupiah. So, we can see that cryptocurrency is not just a trend, but an important part of today's financial system. However, with such rapid growth comes extreme price volatility, which bring both high risk and opportunities for investors. Cryptocurrency itself is a form of digital currency developed using blockchain technology. Because of its decentralized and transparent nature, it is different from the traditional currencies. However, predicting cryptocurrency prices is very challenging because the market is highly dynamic and affected by many nonlinear factors. To handle these kinds of data patterns, we can use deep learning methods. Among them, transformer-based architectures are known to capture long-term dependencies more effectively than older models like RNN or LSTM. According to Vaswani, 2017, the transformer model uses a self-attention mechanism that allows parallel processing and better pattern recognition over long sequences. That's why transformer models are more accurate than traditional statistical approaches such as ARIMA or regression. However, the transformer still has drawbacks. It requires very high computational power and memory, especially when the data sequence is long. It also performs step-by-step decoding, which makes it slower for long-term prediction. To address these problems, Zhou, 2021, proposed a new model called the Informer. The informer uses a proper self-attention mechanism that keeps only the most relevant information, reducing the computational load while maintaining accuracy. It also uses self-attention distilling, which extracts only the dominant information layer by layer, saving memory and speeding up both training and inference. Because of these features, Informer becomes a more optimal solution for long sequence time series forecasting, such as cryptocurrency price prediction. Based on that, in this research, we applied the Informer model to predict cryptocurrency prices. We want to test how well Informer performs when applied to real crypto data, whether it can produce accurate and fast predictions for such volatile markets. So, the goal of our study is to demonstrate that Informer can be used effectively in this domain. Let me show you the sample data used in our study. We used daily price data of 20 different cryptocurrencies, which we collected from the website id.investing.com. The dataset covers the period from January 1, 2016 to February 1, 2025. If some cryptocurrencies didn't exist in the early years, we started from their first available historical record. Each record included opening price, highest and lower price, trading volume, and closing price. But for our analysis, we focus on closing prices because they represent the market's final consensus for the day and are often used for next day prediction. This broad dataset gives a good representation of the crypto market's volatility and allows us to evaluate the model's robustness on different assets. The objective of this research are to develop a cryptocurrency price prediction model using the Informer architecture. The second, to evaluate Informer's performance compared to the Transformer model. And the benefits are, first, to expand the application of Informer in financial forecasting, which has not been widely done before. The second is to test the model using 20 different cryptocurrencies, allowing us to evaluate its performance on datasets with different histories. And finally, to provide insights for investors and analysts to better understand cryptocurrency market dynamics. Previous studies have explored many deep learning models for crypto price prediction. Hamael and Auda in 221 test GRU, LSTM, and BLSTM models for Bitcoin, Litecoin, and Ethereum. They found that GRU gave the best results. Senopati in 224 compared LSTM, BLSTM, ARIMA, and Transformer and found Transformer performed best. Zhou in 2021 introduced the Informer, showing it was faster and more memory efficient while still capturing long-term dependencies. Later, Boget and Nitya in 2024 applied Informer to fields such as stock prices and weather data. And Informer again outperformed other models like LSTM, GRU, and TCN. So, from these findings, we expected that Informer could also work very well for cryptocurrency forecasting. Now, let's take a closer look at the Informer model. Informer is actually a transformer-based model, but it's specifically designed for long sequence time series forecasting. It was created to solve the main weaknesses of the traditional transformer, mainly its high computational cost and memory usage. The Informer improves this with three main innovations that make it much more efficient and scalable for large datasets like cryptocurrency prices. I'll explain each of these innovations one by one. Let's look at how the informer model processes its input. In time series forecasting, it's important to consider not only the numerical values, but also in the time context, like days, weeks, or months. So, informer combines three types of
The time's almost over. Sorry, time almost over. Can you accelerate your presentation? Yes, thank you very much for the second presenter. And anyone has a question? The time is 5 minutes.
Could you please continue? So we still have 5 minutes. You please at least explain the results you get in this research. The results.
Now here we can see the transformer model's training process for comparison. Just like informer, transformer loss also decreases sharply at first and then stabilizes. However, it required more training time and slightly higher loss values than informer. So both models learned well, but informer was more efficient and faster in raising convergence. This slide shows that transformer prediction for the same cryptocurrency. The model also tracked the real prices quite closely, but it was slightly responsive during sudden market change. Compared to informer, the transformer line lags a bit behind in some volatile regions. So while both performed well, informer captured the dynamic movement a little better. Here we summarize the evaluation metrics for both models, MSE, MAE, and MAPE, across all experiments. From the table, we can see that both models achieved their best performance with the 95.5 data speed. Under the setting, informer had MSE of 1,0907, MAE of. This means both models benefited from having a larger training dataset because they learned more historical patterns. But when we look at training efficiency, the difference becomes clear. Informer was significantly faster than transformer. To summarize, the informer model consistently outperformed the transformer in terms of training efficiency and competitive accuracy. Its best results came from the configuration with a 180-day window and 1-day prediction horizon. Achieving MSE, MAE, and MAPE, overall, the longer window size helped the model learn more historical context and make better decisions. So in short, informer proved to be faster, lighter, and nearly as accurate as transformer. That's all for my presentation. Thank you very much.
Thank you very much. And more?
there any
Okay,
question?
I think it's enough. The time is giving the certificate to the presenter. Okay, for the third presenter is B72 with Mr. Muhammad Iqbal, Mr. Mikhail Fizain, and Mr. Ian Hang. With title is Extended Rule-Based and Optimal Action Selection on Reinforcement Learning for Chessboard Game. This is an online presentation.
Hello. Can you hear us?
Yes, we can hear you.
Nice.
Okay. Can we start? I will assume we can.
Yes, please
Maybe.
start. Sure.
Yes.
So yeah, we are gonna present you our research about role-based and reinforcement learning for the chessboard and chess games in general.
So we'll start with the introduction. We will briefly explain how reinforcement learning is used in strategy game, define the problem statement, and present the main research objective of our work. Then we'll move on the methodology section. We'll describe the network architecture, the evaluation function concepts, and how we design the rule-based rewards for the game. We also present the action selection strategy that gets the agent decision during the training. After that, we will look on the evaluation part, where we will present the experimental setup, and we will discuss about the result and the performance that we obtain. And finally, we will conclude with the with the limitation that we face and the result that we have. Sorry. Can move on.
The goal was to create a chess program that is pretty light and pretty easy to train. After we seen like AlphaGo beating the world champion in 2016 at the game of Go and AlphaZero following, we saw that deep neural network started to replace meta heuristic and like get more and more popular. So we tried to implement a model that was easy to train and able to achieve a certain level in chess.
Yeah. So first, we about the problem statement. There were a weak state representation. The general rules aren't very expressive enough to handle complex chess position that we can face off during the game. Secondly, we face subtle action selection. Since using the maximum likelihood estimation alone doesn't always lead us to the best move in such complex environment. And finally, the computation constraint. It makes it difficult to achieve high performances as a training and evaluation model, which require huge computational resources. Sorry.
So yeah, our goal was to create a new type of agent to have the best result in the minimum training. So we redefined some metrics. So we defined some scoreboard for the chessboard in order to take account of those strengths and weakness depending on the position, combined with the recent technologies such as alpha beta pruning and MCTA. So the alpha zero algorithm, and we try to combine them to have the easiest to train model that could also perform at a reasonable level.
So first off, about the architecture, we start with the AlphaGo model, but we find really fast that it wasn't enough for what we want to do, and it was way too difficult for the computational setting. So we move on the model from scratch that we design. So we first with like the input a 12 by 8 and 8 tensor encoding, which represent the chessboard and all the pieces. Then we move on some convolution to spatialize the chessboard and all the pieces. And we have some intention to focus on where are the threats or when we need to focus on part of the board. And then we have some dance to have later an output about the evaluation that gave us about the pieces and the evaluation of the board state.
So after that, we had to evaluate the state of the board. So like who's winning basically? Chess is played by white against black, or 1 versus 1. So in the beginning, it's pretty much equal because the position is symmetrical. So we define the evaluation as the current state by the board of white minus black. And so at the beginning, it's pretty much 0-0. And as we play the game a little bit, we tend to have like some player taking the advantage, and we try to measure that by going on the plus side if white's winning, and on the negative side if black is winning. And this is as a certain depth, so we call it D, which is the amount of moves that can be calculated. And this is how we know the model is playing or not at a certain level. Is it able to make any player better?
So we also gave us some rule-based reward components because each piece have a value, but there are also some position that have a value, like a passed pawn. This is a reward for the pawn with no position, pawn blocking the advance of the path, because a pawn can be promoted for a rook, a queen, or a knight. So the evaluation of the pawn needs to be higher than just one. There will also some strong square because when you defend, it's important to have to control some square because like the center is mainly essential when you play chess. So you need to control all these pieces. So there are strong square that you need to control, and if you control that, you will have some reward. This is the king safety, because if you lose your king, you lose the game. So it's very important to have your king in safety, in safe place, protected by pawn or pieces. We are also some what we call weak point or weak square. This is some pawn difficult to defend or square difficult to handle. So if you have that, you will be penalized. We have also like a rule that says that bishop pair is very strong during the game, mainly during the end game, because you can control all the color of the game. And we are also color complex. This is a little bit more difficult, but this is a reward and a penalty for controlling light or dark square, depend of the where we are in the game. Sometimes it's better to controlling light if you have the white bishop on the white, or dark. It depends.
To select a move, we combine the probability selection and the optimization. Basically, this is the Monte Carlo research. We have to explore moves. So the first part of the model gives us a probability density. That is the probability of each move being the best move in the position. And depending on a parameter that we call beta, we're gonna explore some different moves in order to create different sample of games and try to explore, because chess is a game that cannot be played, cannot be calculated all the way to the end. So we cannot be 100% sure that the move that we chose is the best move in the position. That's why we try to explore with a probability of the move being the best move according to our machine. And it's gonna explore throughout the entire Monte Carlo tree in order to select either the best move, or depending on a certain temperature called beta, a suboptimal move, in order to pretty much see where this is going and have a larger sample of games to train the best. So yeah, that's the different part about like regular engine and this type of engine, the exploration with the temperature beta.
So about the experimentation, we had a training phase with 1,000 epochs with 100 game per epochs on Pygame Simulator. So this is a little bit low for what we could do with such complex like stockfish or whatever. But we tried it. About the evaluation benchmark, we test against Stockfish 16.1. Those Stockfish is the best engine that we can find in the world. So Stockfish was at level 1, 3, 5, 7, and 9. This is only to face Stockfish to see how good the model is. So thanks to that, we had a rating system. So an Elo rating that can train from the 100 game per Stockfish level. So it provides us a rating about our model. And about the experimentation, we fixed the depth of 4 due to the computational processes constraint that we had at the moment.
And the result we got was with a depth of 4, so basically 4 moves ahead, it got 1,000 Elo rating. Elo is how we define chess player, and 1,000 would be like pretty much someone that's starting competition, like the beginning of a competitional player that is not like absolutely insane. For example, Stockfish could be much higher, but given the depth we have and the computational constraint we had, this is actually greater result than anything that could have been achieved before. So yeah, this is definitely encouraging.
So as Jan could say previously, we had some current limitation due to the depth limitation move. For example, Stockfish could have a depth to 20 to 40, even higher during the end game. And to represent like a human can do, professional player can sometimes have a depth of 10 to 20 move ahead. So 4 was really low, but even with 4 move limitation, we could have some results. We also have the current limitation of the high computational requirement for deep research. About the future improvement that we had, we could have some improvement about the opening, because this is one of the more complex part of chess. Sorry. So if we could have pre-trained the model with some opening, the model could be better. We could have also automatic rule generation for weak and strong action, enhance MCT integration, and distribute computing for deep research.
Right. So yeah, that was pretty much our contribution, like achieving a easy to train strong model. Thanks for listening us.
Thank you for the presentation. Anyone has a question? Okay.
Hello, can you hear me?
Yeah, we can.
Yeah.
So on page 8, you explained about rule-based rewards components. So from what I know, usually when we, let's say if we use machine learning, deep learning, and so on, so if we have something, we need to represent them as an equations or formulas. So from the rule-based rewards components on page 8, how do you represent them as equation, or how do you use them in your implementation?
Well, this is created with the probability of winning, actually. The model gives us two data at the end. It gives us the probability of winning, like its evaluation of the position, and a density of moves that, in his opinion, are the best moves. And basically, what we try to do is make this evaluation of how the position looks good to the model as high as possible. And this is by analyzing all the games and analyzing all the results of the previous game he's played.
Okay, I think it's enough. More question? Oh, I think it's enough. Thank you for the presentation.
Thanks.
Thank you very much.
Yeah. Thank you for the presentation.
Okay, so now we will continue to the next presenter. So the next presenter is Ms. Dinita Rahmalia, and the title of her talk is Vehicle Routing Optimization with Customer Clustering and Capacity Constraint Using Wheel Optimization Algorithm. For Ms. Dinita, the stage is yours.
Okay, I will make a presentation with the title is about vehicle routing optimization with customer clustering and capacity constraint using well optimization algorithm by me, Dinita Rahmalia from NTUST, Department of Industrial Management. For the introduction, I will explain the flow process of ordering and delivering the products. It is a basic concept in the supply chain. When the customer order the product, it is usually through retailer, and retailer will order from distributor. And from distributor, maybe it order from the manufacturer, and the reverse is the distributor will deliver the product to the retailer, and retailer will deliver the product to customer. And this is a basic concept in the supply chain process. Next. And the causes of higher transportation cost, because from the distributor, from retailer, deliver the product until reaching customer, the causes of higher transportation cost when delivering products to customers are affected by distance. We can say that the more distance will make the expensive cost, and the routes are not optimal, like from the point this and point there, we use a straight line, and when the roads are not optimal, we can around the route, so that the distance is very large. And I will investigate the effect of capacity of vehicle to the transportation costs and the distance. And the mathematical model of the VRP or vehicle routing problem is like this, with the objective in the equation 1 and the capacity constraint in the constraint equation 2, and equation 3, 4, it is about the vehicle assigned until the decision variable is X, Y, and W. With the set and parameters are the K is the set of vehicle in retailer, S is the distance between customer E to customer G in retailer R, A is the demand of customer E, and CK is maximum capacity of vehicle K, MR is the maximum available vehicle in retailer R with decision variable is X if XEJK, if the customer J is visited from customer E by vehicle K, YKE is the customer I is served by vehicle K, and WKR if the vehicle K is assigned in the retailer R. This is a binary decision variable. Next. The methodology I use in this research is, the first, I generate the demand data and retailer location in the X-min in the -5, and the demand of data is the normally random, normally distributed, with retailer location is in the 4 quadrant, and I cluster the demand based on location X and Y using a simple clustering k-means. And after that, I can find the optimal route vehicle, optimal vehicle routing, use a meta-heuristic algorithm like a well optimization algorithm. And for the VRP or vehicle routing optimization, we divide by 2 cases in the unlimited capacity and limited capacity. And the process of well optimization algorithm, the first is the initialization of population. The initialized population is illustrated in the corner. The first row is the new customer index after clustering. Second row is the global customer index in all location, and third row is the vehicle code. This is an initialization of individual of well optimization algorithm. And the update solution, there are three steps, 3 types in the update solution, like exploration, shrinking, and spiral, because this is adjusted to the whale behavior. And we can compute the fitness function is a distance of the delivering route, and we can find the best solution with minimizing the routes. And whale hunting mechanism is there are parameter initialization like A with A is linearly decreased. It is a wake inertia from 2 to 0, with R is normally distributed from 0 and 1 and A. And this is a exploration phase. This is an algorithm for update solution, exploration, and the shrinking mechanism. Xt plus 1 equals x minus a multiply d. And the third is the spiral mechanism. This is a mechanism of update solution of whale optimization algorithm. And the results is from 4 distributor. This is the left side is the optimization process in the distribution 1, distribution 2, distribution 3, and distribution 4. And the illustration for simulation route is in the right side. We can see that in the maximum iteration 200, it is convergent. But in this distribution 2 and distribution 3 is the fast convergent, because I take the population is very large. It's 100, so that it can convergent fast. And it is a unlimited capacity case. And then if I take the limited capacity 100, the optimization process of WOA is for the 4 distributor is like this, with the illustration in the right side. This is for limited capacity 100, and this is a limited capacity for 200. This is the optimization process and results, and this is for 300. And for the summary of the result, if I type the maximum capacity 100, 200, and 300, the number of required vehicle is the decrease. More capacity in the vehicle can decrease the number of required vehicle, and so the distance will be decreased too. And I also compare WOA, whale optimization algorithm, with the general other meta heuristic like genetic algorithm, PSO, and SEO, and we can see that WOA can improve the solution of the GA, PSO, and SEO. So in the conclusions are meta-heuristic methods such whale optimization can solve vehicle routing problem in case study of product segment to customer with vehicle capacity constraint, and both initialization and update solution steps require modification in whale positions, because the update solution results the non-integer solution. Non-integer solution we need a modification so that satisfy the all constraint. And in the simulation, we try various number of vehicle capacity, and the results show vehicle with larger capacity give less vehicle quantity in shipment process to customer and shorter total distance. And development of the research is by adding more constraints so that it is more challenging to make a computation, incorporating more data, and analyzing with many uncertain conditions and scenario. And the objective is not only about operational costs, but also observe to environmental and social impact and leading to sustainable concept. Thank you.
Okay, thank you for the presentation. So, are there any questions or comments? from the audience? Okay, I will give one question. So we know that from the whale optimization algorithm, there are several operations or mechanisms
Yes.
in the algorithm. How do you make sure that from all the mechanisms, the solutions still will satisfy all the constraints of the original problems? And also you showed in your presentation that in some of the mechanism of the whale optimization algorithm, like I think the one you show for the one you show in the slide is for solving real valued
Yes.
functions.
Yes,
So in your
solve
case,
the-
you deal with vehicle routing problem or traveling salesman problem. So your solution should be an integer solution.
yes.
So I think there should be another version of mechanism. So it's not the same with the real valued functions.
Okay, thank you for the question. I will explain about the three mechanism of whale optimization algorithm. In whale optimization algorithm, there are three update solution in the exploration, shrinking mechanism, and spiral mechanism. But in the three update solution, we need converts from the non-integer to integer, right? Because there is a random variable, random number, so that the results becomes non-integer. And how to solve the integer solution is by giving the new index 1, 2, 3, 4, 5, and we in the first row we sort increasing. In the first law of new customer index, we sort increasing so that the new index will be followed to sorted, and so that we get the new customer index after clustering. It is available. Available for the three update base in WOA. And the second row and third row, the modification is based on information of the first row. This is.
Okay, thank you. Are there any other questions? Okay, so please give an applause to Ms. Dinita. So now we will continue with the next presenter. So the code is P77, and the name of the presenter is Fefi Novkaniza, and it will be online through Zoom.
Okay, thank you. Anyone can hear my voice? Okay, I will start my presentation. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone, distinguished researchers and fellow participants. I'm Fefi Novkaniza from the Department of Mathematics, Universitas Indonesia. Together with Professor Zuhirman Rustam, Dr. Ahmed Ocak Akdemir, and Dr. Hajar Khaloki, I'm pleased to present our study entitled Adaptive Radial Basis Function Kernel in Support Vector Machine. We will propose an optimal method for classifying heterogeneous data with non-uniform distribution. Let's begin by looking at the main motivation behind our research. Traditional kernels assume uniform data distribution, but in reality, datasets often show spatial heterogeneity where density varies across regions. Fixed kernel parameters cannot adapt to these variations, leading to suboptimal margin and overfitting. For example, in medical images, tumor regions are much denser than the healthy tissue, and in the text data, common words dominate while rare words are sparse. To understand our approach, let's recall the basic formulation of SVM. The primal problem aims to find the optimal hyperplane by minimizing the norm of the wake factor while ensuring correct classification. This can be rewritten as the dual problem, which use kernel's function to map data into higher dimension for better separability. Most existing studies overlook the computational challenges of adaptive kernels, especially in edge computing environment. To overcome this, we propose an adaptive radial basis function, or we call ARBF, which adjusts its parameters dynamically based on the local data density. This makes the model more flexible and responsive to heterogeneous data. Here we compare the standard RBF kernel with our proposed ARBF. While the standard RBF uses one global gamma for all data points, the ARBF introduces local parameters that adapt to each point's neighborhood. This allows the kernel to widen in sparse regions and narrow in dense ones, improving flexibility across heterogeneous data. Before introducing our ARBF, let's first understand the data density. The data density measures the concentration of data point within a specific region of the feature space, or it measures how tightly data points are packed in the feature space. High density means points are close together, while low density means they are farther apart. Real-world dataset often mix both, and recognizing this variation is key because they define the data's geometry, motivating the need for an adaptive kernel. Now let's focus on the high-density regions. Here, many data points are closely packed, forming compact clusters with low local variance, as shown in the figure. Mathematically, this means smaller sigma values where the adaptive kernel narrows to capture fine local structure more precisely. In low-density regions, only a few points are spread across a wide area, creating large gaps and high local variance. Mathematically, this corresponds to large sigma values, reflecting low point concentration and irregular neighborhood structures. Such regions are often challenging for traditional kernels, which tend to underfit because they fail to capture this sparse variability. To measure how heterogeneous a dataset, we introduce the density ratio matrix, the ratio between the maximum and the minimum local densities. It will tell us how unevenly the data distributed. A higher ratio means stronger spatial heterogeneity. This helps us to decide when an adaptive kernel is needed, since the uniform dataset behave very differently from highly varied one. In figure A, you can see that each point finds its nearest neighbors to form a local neighborhood. Then in figure B, you can see that the model calculates the local deviation, sigma I, indicating how dense or sparse that region is. Finally, in figure C, you can see that the kernel parameter gamma ij adapt to each pair of points, allowing the ARBF kernel to model heterogeneous data more effectively than the standard ARBF. Let's see how we measure local density in our model. We define sigma I as the average square distance between a point and its k nearest neighbors, effectively capturing how dense or sparse that region is. In our setup, k equals 7, which give a good compromise between local sensitivity and robustness to noise. Here we illustrate how local density is estimated using the nearest neighbors algorithm. Each point identifies its 6 closest neighbors, shown here in blue. The local density parameter sigma I is then computed as the average square distance to these neighbors, effectively describing how tightly the data are clustered around each point. So this is our algorithm. We call it ARBF kernel formation algorithm. The algorithm starts by computing the Euclidean distance matrix for all data points. Then for each point, it calculates the average distance to its nearest neighbors, capturing local density. Using these values, the kernel parameter gamma aj is adjusted adaptively for every pairs of samples, allowing the ARBF kernel to dynamically adapt to heterogeneous data and improve both flexibility and classification performance. Here we explain the adaptive kernel mechanism which serves as the core of the ARBF model. The adaptive parameter gamma ij is defined as the inverse product of the local density sigma I and sigma j, allowing the kernel to automatically adjust its bandwidth. Since the derivative of gamma ij with respect to sigma I is negative, higher density or smaller sigma I makes the kernel sharper, enhancing its local sensitivity. So we take a look now at how the adaptive kernel behaves across dense and sparse region. In dense region, the local deviation sigma I is small, producing larger gamma ij values and sharper kernels with stronger localization. In contrast, in sparse region, sigma I increase, leading to smaller gamma ij values and smoother kernels with broader influence. This dynamic adjustment allows the kernel to balance sensitivity in dense area and generalization in sparse one. So, in our experimental setup, we evaluate the proposed approach using 9 diverse datasets that span multiple domains to ensure robustness and generalizability. For model evaluation, we use 10-fold stratified cross-validation procedure, and the SVM regularization we use C parameter is fixed at 0.8, while for the RBF kernel, the neighborhood size is set to k equals 7, and for comparison, the standard RBF kernel use an optimized gamma values of 0.05. This is the dataset we use, the spanning tabular, image, and complex data type. They range from the small sets like iris and wine to large-scale ones such as minis and 20 newsgroup. The density ratio columns show how concentrated the samples are, ensuring a broad coverage of data, diversity, and complexity. Here we classify dataset based on their degree of heterogeneity. For homogeneous data with uniform distribution, the traditional or the standard RBF kernel works well, like in dataset iris and wine. But for moderate variation, like that diabetes dataset, RBF is recommended. And for highly heterogeneous datasets such as minis and 20 newsgroup, a RBF becomes essential to handle large variation effectively. So this is the table of the benchmark comparison between the adaptive RBF or ARBF and the standard RBF kernels across 9 datasets. Overall, ARBF consistently achieve higher accuracy and F1 scores, particularly on heterogeneous dataset like diabetes, FY people, and 20 news group. The improvement is especially notable where data density varies strongly, confirming RBF adaptability. Although computation or execution times slightly increase for the complex data sets, the gain in predictive performance clearly outweighs the added cost. These figures show the comparison of the classification accuracy between a RBF and the RBF kernel across 9 dataset we use. Overall, a RBF consistently yields higher accuracy, particularly for dataset with heterogeneous or imbalanced distributions such as diabetes, FY people, and 20 news group dataset. While both kernel perform similarly on simpler dataset like wine and digit, the adaptive mechanism of a RBF provides clear improvement when data complexity increases. In this chart, you can see that we compare the computation time between ARBF and the standard RBF kernels. As shown here, ARBF achieve comparable or even faster performance across most datasets. Notably, on the olfactory phase dataset, ARBF runs much faster, demonstrating its efficiency in handling complex and high-dimensional data. Here we can see how ARBF clearly outperformed the standard RBF kernel. ARBF achieved an average accuracy of 92.1%, outperforming RBF by about 2.8%. It performs best on the 20 news group dataset and runs 30% faster on the image data. All improvements are statistically also significant, which p-values below 0.01. As practical recommendation, if you're working with high-dimensional or biomedical data or smaller dataset with uneven distribution, RBF is your go-to. It handles complexity well, but for large uniform dataset or tasks where speed matters, stick with RBF for its simplicity and efficiency. So, in our research, so far, we conclude that from our research, this study demonstrates that the proposed ARBF kernel achieved 2.8% improvement in accuracy and 30% faster on image data. It also shows better generalization and adaptability across diverse datasets. Our main contribution include the first integration of local density adaptation in SVM, a novel theoretical framework, efficient implementation, and also comprehensive validation, confirming its effectiveness. We sincerely thanks to Directorate of Funding and Research Ecosystem Universitas Indonesia for financial support through our research grant. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you for the presentation. And anyone has a question? Question? Okay.
Yes, I have a question.
Oh, okay.
So, Bu Fevi, so
Yes.
Can you please explain again what the adaptive parts in adaptive RBF? So I don't quite get what is the adaptive part in this case. And also on page 21, there is one case where the adaptive RBF is much faster. In olfactory phases. So why does that happen? So it's quite strange. So it is not similar with the other results. So why does that happen?
Okay, thank you for the question. In the Olivetti phase dataset, the dataset is 400 grayscale phase images, each represented by moderately high dimensional vectors. So the Olivetti phases dataset contains well-structured, well-clustered and structured data. So because of this structure, the local density region sigma I values are relatively stable once computed. So the adaptive kernel reuse local density information effectively across similar samples. So because the dataset is well clustered and also structured, that's why the RBF is faster on compared to any datasets. And for your question about our adaptive RBF, you can see that from our formula. So in traditional or standard RBF, the kernel function in gamma is single, or all dataset use gamma parameter for single global parameter. But in our proposed adaptive RBF, we use the local sigma I parameters and also sigma j parameters, and the gamma defined as inverse product of sigma I and sigma j. So we can adapt the local density variation, and it helps our kernel to classify more accurately in support vector machine. I hope it can answer your question, Ms. Pak Lutfi.
Okay, thank you very much.
Correct?
Yes, yes.
Thank you very much for your question, and thank you very much for the committee. Thank you for all participants. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, I think it's enough. Thank you for the presentation, and we will continue to the next presentation with the course P80 with the Mr. Muhammad Iqbal, Mr. Zakaria Elgo, and Mr. Aid Oakley Chalis, with the title is Carbon Price Prediction from Machine and Deep Learning Model, a Comparative Study. Oh, it is online.
Hello again, everyone.
Hello again.
Can you hear us?
Hello.
Okay, nice. So we are gonna replace Zakaria and Jalis because they weren't available today. And yeah, hello again, everyone.
So we'll try to present the work of Chalice and Zakaria. So the work is about the carbon price prediction from machine and deep learning models, a comparative study.
So, given the global warming impact and the climate change and everything that we don't present anymore, carbon prices has been very important, and its prediction is as important, because like controlling the prediction is basically controlling how we use it and how we create it. So the whole motivation was to compare models to have the most accurate way to predict carbon prices rises.
So the research objective is to compare the models between machine learning and deep learning to see what's the best approach for comparing for carbon price prediction. For that, we will use the EEX datasets. So we will analyze European Energy Exchange historical trading data to predict carbon price. And the goal is to identify the best fit, determine which model perform optimally based on the data size and prediction horizons.
So yeah, we are gonna use some from a dataset from November 2021 to June 2024 from the European Union that we carefully selected and normalized to have scaled value between 0 and 1, and then we split the dataset as we usually do, 80% for training, 20% to evaluate the performance of the models.
So for that, we will compare 6 models, three machine learning models and 3 deep learning models. So we have the support vector regression. We'll find the optical function with data tolerance margin using support vector and regulation. We have also random model for random forest and XGBoost. And for the deep learning, we have the RNN, recurrent neural network. We have also LSTM, long short-term memory. So it specializes in RNN, which gate controlling information flow to under long-term dependencies. And we have lastly TACTIS2, so a transformer-based model with attentional computers for multivariate times series prediction.
So we're going to use different metrics, mean squared errors, root mean square errors, mean absolute error, and standard deviation in order to control our results and know which model performs the best and which perform a little bit underneath. And yeah, basically we're trying to get it as low as possible.
So as a result, we can see that we have SVR shows the best results. SVR demonstrates superior performances across all metrics, achieving the lower error values and highest prediction. But on the second hand, we can see that deep learning models in general are better than machine learning, except for SVR.
So here are the results we got. So we can clearly see that SVR performs much better than all the others because the curve in red is basically the test set, so the real data, and the one in blue are the predictions of our model. So we can see that SVR basically fits perfectly, while some deep learning trained model like LSTM, TACTIS2 globally got the trend right. It's globally okay, but you can see that it's not fitting perfectly. And some traditional machine learning like XGBoost or those kind of models are just way off and are not getting decent result at all.
So we can see that there is a dominance about SVR. Super vector regression outperform all the models, including advanced deep learning architecture on our small short data sets. There is a deep learning advantages over the machine learning. And about the data size matter, deep learning models require a larger data set to achieve robust performance and avoid overfitting. So maybe if we had a data set maybe bigger, we could have best results with our machine model or deep learning models.
And that is why SVR performs so well. That's because it doesn't need that much of a big data set. It's designed to be trained with limited samples, and that's what we had. Our data were pretty constrained. So with the short-term prediction and some the SVR got to capture the local patterns with very little data and didn't require much more. So we had some stable and good results without having the downside of requiring huge data sets, and that's why SVR got so good results in this context?
So about the application for the policy market, we can see an accurate short-term carbon price forecast support regulator decision making. A better understanding of the market dynamics aids in emission trading system design. They also improve the risk assessment for climate policy improvements. And for the financial institution, in enhance portfolio management in carbon markets, we reduce investment risk through precise price prediction and strategy advances in emission trading.
So right now we saw that the SVR model is optimal for small scale, small term on the dataset we use, the EEX dataset. And the whole what's at stake basically is to use which model for which dataset given the size or the complexity of the dataset between more conventional machine learning and more advanced deep learning, depending on the size of the dataset we got. And we should investigate how it performs with higher dimensional data sets and more complex, more detailed data, because SVR is great for those kind of small data sets, and we would love to like having put it against much deeper data sets and much complex models of deep learning to see how it goes. Thank you very much for your attention.
Yeah, thank you
Thanks
very
for
much.
listening to us.
Okay, thank you for the presentation. Anyone has question? Okay.
So I have a short question. So
yeah, sure.
Let's for the machine learning part, you choose 3 models, so SVR and what are the other 2? So my question is, why do you choose those 3 models instead of other machine learning models?
Yeah, the models that got chosen were the most popular, basically. We did like quick research and found out that those 3 were in general the one that performed best. So it wouldn't be that useful to use models that in general weren't reputed to perform as good. So yeah, basically we used like the best of all machine learning and the best of all deep learning according to like online studies, and we put it up against each other's to see which ones were the best.
Okay, thank you.
Okay, more question? Oh, okay. And we will continue to the next presenter. Next, thank you for the presentation.
Thank you.
Thank you very much.
Yeah. We will continue to the next presentation with the P50. Mrs. Alvida Mustika Rukmi, Mrs. Faizah Di Anissa, Mr. Muhammad R. Revansa, Mr. Muhammad Iqbal, Mr. Khairul Imron, Mrs. Rinurwati, and Mr. Dharmaji with the title Kidney Disease Diagnosis Model Using Adaptive and SCGCN Transfer Learning Classification Algorithm.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. My name is Faiza Dianisa. We are from ITS. We will present our research titled Kidney Disease Diagnosis Model using Adaptive NSCGCN Transfer Learning Classification Algorithm. Okay, first of all, for background, kidney disease is one of the major global health problems. In Indonesia, there are approximately 200,000 new cases each year, costing around 6.5 trillion rupiah per year. That's why early diagnosis is important to reduce mortality and financial burden. Conventional methods such as biomarkers and artificial neural network are still limited in interpreting the complexity of medical data. This motivates us to find a more effective approach. In AI-based medical diagnosis, two main deep learning models are commonly used. First, CNNs are great for extracting image feature extraction, but they fail to capture relationship between those features. Second, GCNs or graph convolutional networks can model relationships between nodes, but they often suffer from two major issues like overfitting and oversmoothing. So our central question becomes, how can we design a model that overcomes both of these problems simultaneously? Our objective research is to develop an adaptive NSCGCN model, a framework that integrates CNN ability for effective feature extraction and capture feature relationship through GCN, overcome oversmoothing and overfitting simultaneously, and finally improves the accuracy of CT scan-based kidney disease diagnosis. Our contributions is we introduce a novel hybrid framework that simultaneously mitigates overfitting and oversmoothing in GCN-based architecture, and we provide empirical evidence that the proposed model improves diagnostic performance and reduces overfitting, thereby contributing to the development of more reliable AI-driven medical diagnostic tools. Here are our proposed framework. The overall framework of our model consists of three main stages. First, feature extraction using a pre-trained dense net. In the first stage, we employ dense net, CNN architecture known for efficient feature reuse and gradient flow. We remove the fully connected layer to focus on convolutional feature. Dynamic kernel is applied to a depth of receptive area. Attention mechanism highlight important kidney region. Global average pooling is to reduce overfitting. And the output of this stage is discriminative feature map representing kidney pathology patterns. Second stage is feature reconstruction. Next, we convert the extracted feature maps into graph structured data using the neighborhood feature reconstruction algorithm. Here, each node is represent local feature resulting from CNN, while edge capture spatial relationship between nodes. This structure maintains the complex spatial structure of the kidney and allows the GCN to understand contextual relationship between different regions. In the final stage, we use the neighborhood subgraph correlation graph convolutional network, or NSE-GCN. The NSE component reduces feature dimension and kernel parameters, helping to mitigate oversmoothing. Meanwhile, the GCN component model relationship between nodes. The GCN components model relationship between nodes. Finally, a fully connected layer and global average pooling perform the classification into 4 categories: normal, cyst, tumor, and stone. We train and evaluate our model using the CT kidney dataset from Kaggle. It contains 12,446 CT scan image divided into 4 classes: normal, cyst, tumor, and stone, with resolution ranging from 512 times 512 to 858 times 1060 pixels. For training, we use transfer learning by freezing dense net. For training, we use transfer learning by freezing dense net, pre-train layers, and set the parameter as follows. The first experiment using dense net for feature extraction.
Can you accelerate your presentation?
Here are loss and accuracy curve of dense net in training and validation. Next, we compare two graph connectivity structure for neighborhood and edge neighborhood, and for neighborhood connectivity more stable and minimal overfitting. Next, we test in different learning rates. A learning rate of 0.0001 achieved the most stable and optimal convergence. And final model performance evaluation, we achieved accuracy 91.98% and 85.15% for precision, sensitivity, and F1 score. Okay, to demonstrate real-world usability, we implement a prototype prediction system based on our trained model. User can upload a CT scan image and obtain automated prediction of kidney condition. For conclusion, adaptive NSE-GCN was successful in overcoming oversmoothing and overfitting, and improving diagnosis accuracy to 91.98% and providing stable result on CT scan datasets. For future work, it can be trials on real clinical data, integration of multimodal data, optimization for real-time medical device. Okay. AI plus graph is equal to future of medical diagnosis. Thank you.
Thank you. Any question?
Okay, I have a question. So in one part of your presentation, you said that you read FC, so I assume it is a fully connected layer. So you remove FC layer, and then you write, you want to focus on the convolutional part. So my question is, why do you remove the fully connected layer? Because from my knowledge, in almost every deep learning, we always use fully connected layer in the last part.
Okay, thank you for question. In the end of stage 1, fully connected layer is removed and changed by global average pooling to reduce overfitting.
So are you sure that this implementation is correct? I mean, are you sure that when we remove the fully connected layer and we use global average pooling, then we will reduce the overfitting? I mean, is it always correct like that?
Here we modify the dense net architecture so that in the final before future map, this is global average pooling.
Okay, thank you.
Okay, thank you. And I think is enough. It is time for the giving certificate to the presenter. Thank you for the presentation, and we will continue to the next presentation. The code P53 by Mrs. Iha Magdalena and Mrs. Fauren Ahansa with the title Optimizing the Wave Transmission Coefficient in Breakwater and Trench System.
Okay, good afternoon everyone. My name is Farana Tirakanza. I'm from Bandung Institute of Technology. And let me introduce my topic first. You guys probably heard about Apple's new earphone, the one that have a feature called noise cancellations that adjust to block out unwanted sound. Here, I do the same thing, but not with the noise, not with the sound, it with the oceans. Instead of canceling noise, we're canceling wave energy before it reaches the land. By pairing a submerged breakwater and trench, we can tune how the sea floor interact with the wave, just like earphone interact with the sound. Same goal, calmer experience, but not for your ear, it's for the shoreline. Let me start with why this matters. In Southeast Asia, especially in Indonesia, Philippines, Thailand, the coastal regions are under serious threat. Sea levels are rising, storms getting stronger, and shorelines are disappearing faster than ever. In Jakarta, for example, the coastline retreats by about 1.2 meters per year. For millions of people who live near the sea, the protection isn't optional, it's urgent. That's why engineering and researchers rethinking how can we reduce the wave energy before it reaches the land. One of the most simplest ways to protect coastline is by reshaping the seabed itself. Submerged breakwater and trenches act as a silent defense that weaken the wave energy before it reaches the land. Under ideal conditions, a breakwater can reduce wave energy by up to 70%, and trenches is about to 50%. But here the catch. Most the study analyze them separately in isolations. In the study, we take one further step. How if we combine them? How if we optimize their geometry to minimize the KT, or the wave transmission coefficient? To answer our main questions, we first need a model that captures how waves move into the changing depth. The objective of this study is to find the optimal configurations of breakwater trench that minimize the wave transmission coefficient. We use one-dimensional shallow water equations as our foundations, since they describe how long small amplitude wave evolve over variable depth. The domain is divided into 4 regions. Okay. The incoming wave zone, the number 1, the breakwater, number 2, the trenches, number 3, and the shore-facing zone, number 4. In the last regions, we assume an absorbing boundary, so the wave energy does not reflect back, allowing us to focus purely on how geometry controls the transmission. After defining the model, we solve the equation analytically by assuming harmonic wave for both surface elevations and velocity. This assumption turns the shallow water equations into a simple set of relationships that describe forward and backward wave in each region. Each segment of the domain, the incoming wave, the breakwater, the trench, the transmitted zone, has its own pair of wave components. This piecewise solution representations the basis of calculating how the wave transforms as it moves toward the different domain, into one domain into another. At the boundaries between each region, we apply continuity conditions so that both surface elevations and velocity remain smooth across the interface. This condition forms a linear system that connects all wave amplitudes, including the transmitted one. Once it's solved, we can calculate the transmission coefficient, which is the ratio the transmitted wave amplitude and the incident wave amplitude. By expressing KT as a function of the four main design parameters, the two depth and the two lengths, we can then perform optimizations to find the configurations that minimize KT or the wave transmission coefficient. This analytical framework gives us the baseline solution before we validate it numerically. After obtaining the analytical model, we also solve the same equation numerically to verify and refine the results. Here we use the Lex-Wendorf scheme, which is the second order occurred in time and space. In this grid, the red nodes represent the surface elevations, while the blue ones show velocity. Both updated alternately as the wave moves through each region. This numerical setup allows us to visualize how optimized configuration performs dynamically and to confirm that the analytical predictions of KT are accurate in real-time simulations. Here we compare the four main cases to see how each configurations affect the wave transmission. If we look at the baseline, the wave transmitted amplitude is 1. It's the same of the wave amplitude in this incident before the structural. But in the baseline, the structural is a flat bottom, so it makes sense. In the trench only, the transmission amplitude is 0.99. So it reduced the wave energy, but only a few. Meanwhile, in the breakwater only, it's 0.97. It's reduced wave energy, but yes, only a few. Finally, the breakwater trench, the transmitted amplitude is 0.96. It reduced about 3.6% of the incident wave amplitude. So, the pairing of breakwater and trench provides stronger wave attenuations by combining reflections and phase control, resulting in noticeable in KT. Okay, here we analyze how changing breakwater depths, H1, affect wave transmission. On the left, we test it without trench, and on the right, on the right we test without trench, and on the left is with trench. Both analytical and numerical curve align very closely, showing consistent results. When there's no trench, KT has a shallow minimum around 0.69. But once we add the trench, the minimum KT dropped further, down about 0.58 at an optimal breakwater of 1.64 meters. This means that the combinations of a shallower breakwater and a deeper trench creates better reflection phase balance, giving stronger and more stable wave attenuation.
Time almost over. Can you accelerate?
Next, we vary trench depth, H2. On the left is with breakwater, and on the right side, it's without a breakwater. In both cases, as the trench becomes deeper, KT steadily decreases, meaning less wave energy passes through. This shows that increasing the trench depth enhances phase adjustment and strength distributive inference, allowing deeper trenches to achieve smaller KT and better overall attenuations. Finally, we vary the width parameters, L1 and L2. L1 is the breakwater and L2 is the trench, to see how the length of each structure affect the transmission. Unlike depth, KT doesn't change smoothly, it oscillates, forming repeated peaks and valleys that correspond to constructive and destructive interference. Both the analytical and numerical results show the same pattern with a small error. The lowest KT occurs around 5.55 meters, and L2 is about 14.23 meters. This means jointly tuning both lengths achieve better wave reduction than adjusting either one length. Okay, so the conclusion is The analytical and numerical models consistently capture wave transmission behavior across the combined breakwater trench system. The Lex-Wandowski maintains high accuracy with the analytical numerical difference typically below 0.5% near the optimal configurations. Structural depth strongly governs attenuation. Shallow breakwater and deeper trench yield lower wave transmission. Structural lengths introduce interference effect, give critical minima of transmission. Here's the reference that I use. Thank you very much.
Okay, thank you for the presentation and question. Oh, okay.
Thank you for your presentation. I have a question. At governance model slide, you said that you use the submerged breakwater and trench. Can I ask why you choose the submerged breakwater placed in subdomain 2 while the trench placed in subdomain 3? What happened if you change the system placed? Thank you.
Okay, thank you. Okay, maybe I'm gonna answer it. So when the wave came into the breakwater, the wave become slower because there is changing depth. And then after that, the wave energy it's reduced half. So when the wave energy came into the trench, it's become faster because the changing depths again. And then when it comes to the zone 4, it become slower again because there is changing depths again. But if we use these configurations, the wave that after breakwater and the wave before the trench end, it become cancel each other. So the wave that come into the land, it's lower than the incoming wave. That's why I put the breakwater first and the trench. But if I put the trench first, then the breakwater, maybe it will works, but on different depths and length, not the same for these configurations. Maybe it will good for next research, I think. Thank you.
Oh.
May I ask a question?
Oh, okay. One more question.
Okay.
So in one of your slides, you want to get the best setting for H1, H2, L1, and L2, and then in the next slide you do sensitivity analysis on all of the parameters. So you do sensitivity analysis on each one of the parameters. I mean, you do it on H1 only, and then you do it on H2, and then you do it on L1 and L2.
Yes.
So, and then in your conclusion, you give the best setting for H1, H2, L1, and L2. So my question is it correct to do it like this? So you do it one by one, H1 only, H2 only, L1 and L2, and then you conclude from this, you conclude the best setting, or should maybe can you try to optimize all of them, H1, H2, L1, L2 together, instead of doing it one by one?
Okay, let me answer that questions. So in this research, I just turn them like individually, especially in the depth and the width. Maybe I can try in all by together, but I think it's better when I knew the individually first before I came to simulation them together. But in this research, I didn't simulate them together, so I just do look at them separately. But I use this parameters when the others I variated. That's all.
Okay, thank you.
Okay, thank you.
Okay, thank you. I think it is enough. It is time for giving the certificate. Okay, we will continue to the next presentation, P54, Mrs. Ika Magdalena, Mrs. Esther Wahyuningsi, and Kanan Akoluniu with the title Numerical Simulation of the Chiral Nonlinear Schrodinger Equation using Runge-Kutta and Predictor-Corrector Models.
Okay. Hello everyone. Before we started, I want to give you the question about these two pictures. What's the difference between them? Let's look closely at these two waves. One in the top, we can see that the wave is symmetrical, predictable, and reversible. But in the other, we can see that the wave is directional, twisted, and asymmetric. In classical physics, we often think that wave is balanced. Nature is balanced. But what if it isn't? What if wave doesn't symmetric as we think? This is the chirality breaks and the chirality and the symmetric breaks. And today, I would like to take you into that world where chirality can change the wave move. So, hello everyone. I'm Esther Wahyuningsi from Institut Teknologi Bandung. It's a great honor to stand here and present our work today titled Numerical Simulation of the Chiral Nonlinear Schrodinger Equation in collaboration with Dr. Ika Magdalena from ITB and joint work with Kanan Akoyunlu from Istanbul Culture University. So, I won't start with the soliton. The wave packets that travel long distance without changing their shape and always maintain their amplitude. The behavior of the classically soliton described by the nonlinear Schrodinger equation that captures the balance between the dispersion and the nonlinearity. But when we added the chirality into that wave, what happens when chirality makes the medium asymmetric? So here's the thing. In reality, the plasmas, both end-stain and the fiber, behave differently, behave the asymmetric. So to capture the asymmetric, to capture the chirality, we extend the nonlinear Schrodinger equation by adding the chiral system, a chiral term, forming as the chiral nonlinear Schrodinger equation. So on this research, we want to develop the Runge-Kutta method and the predictor-corrector method for the CNLS. And then we accurately simulate the bright and dark and also the interaction of two bright soliton. And then we validate accuracy using the RMSE. And last, we want to achieve the computational efficiency through the time performance. So to solve the problem, we use the chiral nonlinear Schrodinger equation. We can see the formula in the slide, which lambda is the complex valued, and then C star is the complex conjugate of C, and lambda is the nonlinear coupling constant. Okay, we developed 3 types of soliton. The first is the bright soliton, mathematically described by second hyperbolic, lambda positive, and localized pulse on zero background. And then the second is the dark soliton, tan hyperbolic. We can see the lambda is negative, is defocusing the nonlinearity. And the last is the interaction of 2 bright solitons to see the elastic of the soliton behavior. Okay, let's move into the method. We start with PDS system, and then we decompose into the real and imaginary parts, and then we spatial discretization with high order central finite difference, and then we transform into ODE system, and the last, we use the time integration using Rungakuta and the predictor corrector. Okay, let's move into the numerical model. The first is the 4th order for the method. It's 4th order Rungakuta. We use the classical 4th order Rungakuta method. It calculates for intermediate states in every time step to produce a highly accurate update. Although Rungakuta is explicit and stable, it requires multiple function evaluation, which increase computational cost. However, it is very reliable for validating the accuracy of our simulation. To improve the efficiency, we also implement the 4th order predictor corrector scheme. The first 3 steps is using Rungakuta, and then we use Adams-Basford for the predictor, then and Adams-Moulton as the corrector. The multi-step of this approach significantly reduces the number of function evaluation, which makes it more computational efficient while maintaining the high accuracy. This comparison between Rungakuta and predictor corrector as one of the key objects of this work. So let's move into the result. We start to simulate the bright soliton, that localized wave peak expected as the result. As we can see in the 1-dimensional, 3rd-dimensional, and surface plot, the wave peak propagates without dispersion or distortion. The bright soliton can maintain their amplitude. This confirms that both Rungakuta and predictor corrector preserve the localized structure of the soliton under focusing the nonlinearity. Okay, to verify the accuracy of the bright soliton, we compare to the numerical and analytical solution, and we can see from the plot and from the RMSE analysis that the root mean square error remains extremely low for both Rungakuta and predictor corrector, indicating excellent agreement with the analytical solution. Although Rungakuta and predictor corrector has a similar accuracy, the predictor corrector method is slightly more efficient in terms of computational time, making it advantage of the long time simulation. So next, we simulate a dark soliton, which is fundamentally different from the bright soliton, and we focus to defocusing the nonlinearity, as the result. In 1-dimensional, 3-dimensional, and surface plot, we can see that the depth and width through the propagation is very good, demonstrating that our numerical schemes can robust handle the non-zero boundary condition. To verify the accuracy of the dark soliton, we same as the bright soliton, we compare at the numerical and analytical soliton at t equals 10. And we can see from the plot and from the RMSE analysis that both Rungakuta and predictor corrector, confirming the schemes accurately capture the defocusing of nonlinearity or the defocusing of the dynamics. And for the time, computationally, same as before, predictor corrector approach delivers comparable accuracy with better computational. And the last, for the interaction of two bright soliton, we can see the simulation or the plot that initially the two soliton are well separated and propagate toward each other. During the collision, a strong nonlinear interaction occurs, momentarily distorting their profiles. After the interaction, both soliton recover their original shapes and velocities, clearly illustrating the elastic nature of soliton collision. For the last, we evaluate the performance of the interaction to bright soliton, and then we can see from the plot and from the RMSE that the both schemes maintain very low error through the collision, confirming the stability during highly nonlinear events and can give the insight that the soliton is elastic. So here we summarize the RMSA result and computational time across all simulation, bright soliton, dark soliton, and two interaction of two bright soliton. We observe that Rungakuta and predictor corrector consistently achieve very low RMSE, confirming high numerical accuracy. In terms of computational performance, the predictor corrector method requires fewer function evolution, making it slightly faster than Rungakuta, especially in long time propagation. This demonstrates that predictor corrector offers a practical balance between accuracy and efficiency. To conclude, this study successfully implemented two fourth-order time integration schemes, Rungakuta and predictor corrector, for solving the chiral nonlinear Schrödinger equation. Both methods accurately capture the soliton propagation, including bright, dark, and two interaction of bright soliton, with minimal distortion or dispersion. Validation using RMSE confirmed the reliability and stability of both schemes. While Rungakuta remains robust and stable, the predictor corrector method demonstrated a computational advantage, making it more suitable for extended simulation of asymmetric wave dynamics. Overall, this result that I presented provide a solid numerical foundation for future exploration of higher dimensional chiral nonlinear Schrödinger equation problems or more complex chiral wave phenomena. So this is my references I used. So that's all from me. Thank you for your attention.
Okay, thank you for the presentation. And any question?
Thank you for the presentation. In your research, you developed three types of solution, right? It is a bright solution, dark solution, and interaction of two bright solution. Can you give us the different or behavior of each solution, like bright, dark, and two interaction? Thank you.
Okay, thank you for the great question. Wait. Let's move into the physical plots. Okay, thank you for the great question. What's the difference between bright, dark, and two interaction of the soliton I presented? The first is the bright. We can see physically in the plot that the bright soliton focusing the nonlinearity with lambda positive and focus on the nonlinearity. The bright localized pulse on zero background. For the dark soliton, we can see physically to defocusing non-linearity. So in dark soliton, we focus on a deep or a depth in ocean or on in wave. And then for the dark soliton, we use lambda negative. And the last, for the interaction of two bright soliton, we can see that two waves propagate each other. During the collision, they interact the nonlinearity of the collision. They interact the nonlinearity, and after they interact each other, they re-emerge with their shape or their original shape. It is demonstrate the elastic of the soliton. That's all.
Other question? Okay, okay. Huh? Oh, okay.
So could you please explain again, why do we need to add chirality to the nonlinear Schrödinger equation? So what problem we have with the original analysis? Thank you.
Okay, thank you for the question. As I presenting in the introduction, we can see that the wave in real system is not symmetric, nature is not also symmetric, but there are the wave that asymmetric or chirality. So example like Bose-Einstein, plasmas, or fiber, it's not a symmetric wave. And to solve that problem, we added the chiral system, the chiral term to the Schrödinger equation. So to answer it, we use the chiral nonlinear Schrödinger equation to solve the problem. That's all.
Okay, thank you for the answer. I think it's enough. This is giving the certificate.
Thank you.
Thank you. Thank you for the presentation. And the next presentation is the P33 by Mrs. Mona Lisa Eri Jolly, Mr. L. Hari Wiryanto, and Mrs. Ika Magdalena with the title A Lax Scheme Analysis of Dumpling Problems in the Green-Nadi Framework.
Okay, thank you for the opportunity given to me. Good afternoon, everyone. My name is Mona Lisa Rijoli. I'm from Institute Teknologi Bandung. Now I will present our research with the title The Lax Scheme Analysis of Dumpling Problem in the Green-Nadi Framework, with collaboration with my supervisor, Professor Leo Wiryanto and Dr. Ika Magdalena. This is our outline of my presentation. Introduction, Green-Nadi model, Lax scheme, and numerical solution, and the last is conclusion. Dam construction carries a high level of low risk because there is always possibility
of damage control structural failures. The phenomenon is known as dam break. It even can cause several damage to downstream infrastructure and the ecosystem, primarily due to erosion and the sediment transportation. Consequently, dam walls has become benchmark the case in coastal and maritime hydrodynamics, widely used for the validation of numerical and experimental model. Because the dam break event can have serious consequences, many research have attempted to simulate this phenomenon. However, classical hydrodynamic models such as Shellwater equation often fail to capture the complex and non-hydrostatic characteristic of the phenomenon like this dam break event, because Shellwater equation do not account for non-hydrostatic pressure and wave diffraction. To address this limit, more models have been to default better describe the nonlinear and non-descriptive characteristic of the dam break flows. One is the Grignardi model, because the Grignardi model ability to describe non-dispersive and wave profile effectively make it the powerful tools for the hydrodynamic studies. We know Grignardi model equations are nonlinear, requiring to stable and efficient numerical method for their solution. And then definite different method has chosen for simply and accuracy for fluid flow problems. Among the finite different method variants, the LEXCAM, I think it's well known as an explicit conservation to characteristic of damage flow in handling discontinue and shock wave. This study aims to evaluate the problem and the stability and accuracy of the LEXCAM in solving the one-dimension non-descriptive Grignardi model for dam break problem under both conditions. The one condition is a wet bed and the two condition is the dry bed condition. And this is the formulation or general formulation from the level 1 Grignardi model. The basic equation includes the mass and the momentum equation for you can see in the equation 1 until equation 3. By assuming that horizontal velocity is the uniform over the deep and the interchange vertical from the bottom to the free surface, and the conservation of the level 1 Grignardi model is obtained by mass and momentum conservation as shown in the equation 4 and equation 5. Where H is total water depth, U0 is the uniform horizontal velocity, and B1, B2, and B3 is the term dispersive. In this study, the terms are set to 0. To solve the Grignardi model and explicit the finite different method based on the LEXCAM is applied. The general discrete from the LEXCAM has shown in equation 6, and the discrete equation are applied to mass and the momentum conservation as shown in the equation 7 and equation 8, where U is the vector of the conserved variable, and Fu is the flux factor, which is a function of U. And then velocity is at its grid point, update with this equation, and the stability numerical model, our check in using the Von-Neumann stability analysis, then which given the CFL condition, you can see it in the question 10. Now, next to the numerical solution. The numerical solution, we are carry about for one-dimensional Damrik problem under two scenario. One scenario is wet bed condition where the finite downstream where depth exists. You can see in figure 1, HU is the dream water depth and HU is upstream water depth and SD is downstream water depth. And second condition or second scenario is the Dybert condition where downstream water is 0 or negative. This is the initial condition we use, and boundary condition is eta or the water surface elevation is keep constant and the momentum is set to 0. The simulation of the one scenario of the bed Damrik was done using the several reference parameter. The channel length was set as 50 and the position of them is set 25 and then one step and the D0 is 0.01 and the HU or upstream deep water is 1. The condition is test for the 2. The downstream condition is 0.5 and 0.2. Now to validate the numerical result, we use the analytical solution developed by Mukasey. You can see in equation 2012, 23, 24, 15, and 2015. And this is the simulation down condition for its 0.5 for the times 5, 7, 10, and 15. And then this is the accuracy or validity of the simulation. Use the RMSE for HD, you can see in the slide. And then this is the down condition for HD 0.2. It's same with the 0.5. Actually, there is not different with the scenario had bad HD 0.5. And this is the numerical simulation for second scenario dry bed condition where the after the dam is not water. And I use the HD set for 10 power minus 6 ini for the times 5, 7, 10, and 15. The simulasi results show that the water surface profile match the analytical solution very well. And then you can see at the time 15.5, the error becomes smaller again, show that the numerical model is stable and accurate. And the conclusion of our research, this study, I think this important, this study successfully investigate the dynamic of Darman problem stroke numerical solution using the non-dispersive gene model combined the LEX-CAM. Overall, the finding demonstrate the LEX-CAM when applied to non-dispersive Grignardi model suffers efficient and robust numerical approach for the modeling fast, non-linear and non-dispersive, then break fall under the various bad conditions. This is our reference, and thank you.
Okay, thank you for the presentation. The question?
Okay, thank you. So the question is, in your research, the dispersive terms in the Grignardi model were set to 0. Can this research be further developed by including non-zero dispersive terms? If so, can the LEX method still be used to solve the equations? Thank you.
Thank you for the great question. Yes, I think this research can be further developed by including non-zero dispersive term in Grignardi model. Actually, certainly working this continue about this research by editing the dispersive term, the model able to capture angular lure like the shock wave in the dam break problem, and more complex wave shape variants that occur after the dam break. However, I think numerical method used is not longer by the LEX-CAM, but rather the development, the LEX-CAM with the developed by the Lex-Wendroff. You know, the Lex-Wendroff more it's effective to handle the high level order because B1, B2, and B3 is the high order on the gene on Grignardi model. I think this. Thank you.
Okay, thank you. Next question. Okay, I think it's enough. Thank you. It is for giving certificate. Okay, thank you for the presentation. And the last presentation is B41 by Mrs. Ika Magdalena and Mrs. Hasnaya S. Kailasani with the title Synergistic Effect of Seagrass and Submerged Breakwater in Enhancing Wave Attenuation.
Imagine standing on the beach in Indonesia in the year 2100. The sea has risen more 30 centimeters. Waves are stronger, coastline and eroding, and communities are forced to leave their home. This is not this distant possibility. It is a projection supported by scientific report. Face this challenge, Indonesia needs a strategy that can truly protect our coast. Therefore, good afternoon, distinguished committee member and fellow researcher. My name is Kasnaya Safakalasani, a graduate mathematics student from Bandung Institute of Technology. I'm honored to present you my research about synergetic effect of seagrass and submerged breakwater in enhancing wave attenuation conducted under supervised Dr. Ika Magdalena. Let me begin with the context. One of the biggest impact of climate change is sea level rise. In ASEAN country, this proof is already visible, such as in Philippines, sea level rise can affect the coastal aquifer. In Indonesia, it can destruct of coastal ecosystem, displacement of coastal communities, and damage the coastal infrastructure. In Singapore, 30% of the island are less than 5 meters above mean sea level. Then, in Cambodia, this country could lose their 25,000 hectares of agriculture in every 1 meter sea level rise. So, this shows the urgency of protecting our coast. With one of the world's most extensive coastline, Indonesia faces unique challenges. Protection of this coastal area is urgent, not only for ecological preservation, but also for social and economic stability. Given this challenge, Indonesia needs effective solution with submerged breakwater and seagrass to robust the coastal protection strategies. The wave propagation model can be seen using the shallow water equation, or SWE, that describe the horizontal propagation of gravity and inertia gravity wave. We applied the mass conservation and the momentum conservation with the modification including the friction coefficient. And for our computational model was divided into 5 subdomains with an absorbing boundary on the right side. The submerged breakwater is placed in subdomain 2, meanwhile the seagrass is placed in subdomain 4. Using the method of separation variable, we assume the monochromatic wave with specific frequency omega. By substitute the expression into SWE, we will get the differential equation. After that, we will derive for both analytical expression, wave height and wave velocity using eta, xt, and uxt in each subdomain. At this continuous point, or such as between each domain, we enforce the continuity of wave height and horizontal momentum. From this condition, we will derive the wave transmission coefficient, or denoted as KT. This transmission coefficient is essential, tells us how much the wave was transmitted through the system. So, indicates the effectiveness of our model. According to its definition, the wave transmission coefficient can be expressed mathematically as ratio transmitted amplitude and initial amplitude. Or for our model, the KT can be expressed with this equation. To complement the analytical solution, we developed the numerical method using finite volume method. This method is suitable for this case because it has no damping error. A staggered grid is adopted where the mass conservation and the water height discretized in the cell center xj. Meanwhile, the momentum conservation is discretized in the cell center xj plus 1/2. Then, we also applied the forward in time and center space sim with this mass conservation and momentum conservation equation. To handle the affection, we applied the upwind approximation where the calculation of water height in spatial j plus 1/2 will depend on the local water velocity. Then we perform the numerical simulation using this chosen parameter in this table. The analytical wave transmission coefficient and the numerical wave transmission are closely around 0.71 that has an absolute error 0.34%. That has a strong agreement that the analytical solution and numerical solution is close. Then the wave height reduction is more than 30% using combination of seagrass and submerged breakwater. Then we perform the sensitivity analysis of KT. First, we variate the friction coefficient of submerged breakwater and seagrass. From this figure, we can see that an increasement of friction coefficient will reduce the transmission coefficient, leading to decrease in wave amplitude. Second, we variate the length of breakwater and seagrass. A longer breakwater and seagrass will decrease the transmission coefficient, enhancing the wave attenuation effect. Last, we variate the height of the breakwater. Consistent with the previous parameter, a higher breakwater will make the transmission coefficient value lower, resulting in the greater wave amplitude attenuation. So, for validate our model, we conduct the experimental verification at the Wave Laboratory at Bandung Institute of Technology, May 2025. The experiment setup was include the wave loom, submerged breakwater, and the vegetation. From the result, it can say that our developed numerical sim can calculate the transmission coefficient successfully with an error 3.9% that compared to the experimental KT. For close my presentation, these are some concluding remarks. First, the shallow water equation with staggered grid finite volume method accurately capture wave damping phenomena up to 30% by combination of seagrass and submerged breakwater. 2. The numerical solution closely approximate the analytical method yielding an absolute error 0.34%. Last, the wave transmission are successfully reduced indicating by increasing the structural length, height, and friction coefficient. This presentation based on the ASEAN report, shallow water equation literature, and the recent analytical and numerical studies. Thank you for your attention. Maybe any feedback or question is I welcome.
Okay, thank you for the presentation and the question.
Okay, thank you for the presentation. It's interesting topic. At numerical method, you said you choose the upwind approximation. So the question from me is, why you choose upwind method to approximate the V, or you say in the presentation the water height?
Okay, thank you for your question. Maybe I will answer with this slide. The upwind approximation is used well to find the water height in the spatial J plus 1/2. Depend on the local water velocity. When you see if the U is bigger than 0, the water height will compute with the previous spatial or forward in time and backward in spatial. Meanwhile, if the water velocity is lower than 0, the water height will calculate after the spatial. So we will apply the forward in time and forward in space. Maybe is it answered with this my? Thank you for your question.
Okay, I think is enough. I think it's enough, and thank you for the presentation, and I will give you a certificate. Okay, we all have finished all presentation for the room 2, and this the next.
Okay, before we end this session, I want to thank a massive thank you to our incredible moderator, Ms. Dinita Rahmalia, and to all of you, our amazing presenter. And then thank you for joining this parallel session. And now we are heading into our closing ceremony. Please stay here in the main ballroom and enjoy the rest of the conference. Thank you.
Recording in progress.
Ladies and gentlemen, please come back to the ballroom so we can continue to our main agenda, please.
Ladies and gentlemen, please come back to the conference room as we are about to start the next agenda.
Welcome back, everyone. We hope you enjoyed the discussion sessions and had an insightful exchange with your groups.
Ladies and gentlemen, after a series of intensive and thought-provoking parallel sessions, it is time for us to take a short moment to relax and enjoy a touch of Indonesia's rich culture.
To refresh our mind, we are delighted to present a special performance by mathematics ITS students Tari Condong.
beber bidak kuye anak bidak melayang
What a beautiful performance. Let's give another warm round of applause to our talented dancers.
Before we conclude, it's time for one of the most awaited parts of today's program, the awarding session.
This afternoon, we will be announcing the top 3 Best Paper and Best Presenter awards. These awards recognize excellence, clarity, and contribution to the field. To the award recipients, please come forward to the stage to receive your award.
For the pure math best paper category, the award goes to
Muhammad Zulfikri Zufar, Muhammad Shifaul Mufid, Diki Azkia, Kistosil Fahim, Wahyu Fistia, Doctorina.
for their paper on the Latin square group over max plus algebra. For the applied math best category, the award goes to
Fitri Cahyani, Ahmad Sultani, and Cynthia Meninda Anjani.
for their paper on dynamical model of recrudescent in Plasmodium falciparum in Indonesia. And for the best computational math paper category, the award goes to
Bandung Ari Sanjoyo, Mahmud Yunus, and Nurul Hidayat.
for their paper on a new initial approximation bound in the Durand-Kerner algorithm for finding polynomial zeros. To present the awards, we are honored to invite Dr. Didik Hasnul Arif, Head of Mathematics of Department at ITS. To Dr. Derek, please come to the stage to give the award. Next, we will continue with the Best Presenter Awards. For the Pure Math Presenter category, the award goes to
Nafa Shibli.
for the paper on polynomial invariance of quasi alternating maths.
For the applied math category, the best presenter award goes to Esther Wahyuningsih.
And for the best computational math presenter category, the award goes to
Fevi Novkariza.
To present the awards, we are honored to invite Dr. Mohammad Iqbal, Chairman of ICoMPAC 2025. Dr. Iqbal, please come up to the stage to give the awards. Congratulations to all award recipients. Your hard work and dedication truly represent the spirit of academic excellence we celebrate at ICoMPAC.
Let's give another big round of applause to the awardees and all participants for their hard work and dedication, because every single one of you made this conference meaningful.
Before we move on, we would like to share some additional information for our participants.
First, there will be a promo tour tonight, and for those of you who have already registered, please gather at the lobby of Oakwood Hotel or Sheraton Hotel at 10:30 p.m. For those who have not registered but are interested in joining in, you may still register at the registration desk today.
We would also like to inform you that there will be 2 data science workshops on Friday, October 24th at 9 a.m. held at the Mathematics Department at ITS.
The first workshop is Introduction to Indoor Positioning Development by Professor Zhongshu Liu for National Taiwan University of Science and Technology.
And the second workshop will be a few attempts in model explainability and trustworthy AI by Professor Pao from National Taiwan University of Science and Technology. These workshops are open for all participants and are a great opportunity to gain new insights in the field of data science. So, we highly encourage all participants to join.
And lastly, for participants without paper submission, you may collect your certification at the registration desk.
As we reach the end of ICoMPAC 2025, let's take a moment to appreciate the knowledge, ideas, and connection we have shared throughout the day.
Through the opening remarks, keynote talks, and paper presentations, we have seen how mathematics continues to play a vital role in addressing complex global issues, especially in sustainability, technology, and innovation.
The discussion today showed how collaboration and knowledge exchange remain essential to scientific progress.
On behalf of the organizing committee, I would like to thank all speakers, presenters, moderators, participants, and sponsors for making ICoMPAC 2025 a success. Your presence and contributions are deeply appreciated. I am Silma.
And I am Charles, and it has been our pleasure to serve as your MC today. We wish you continued success in your research and look forward to seeing you at the next ICoMPAC.
Once again, thank you for attending ICoMPAC 2025. See you on ICoMPAC 2027 in Japan!